Oh, okay. So, well, welcome everybody to this year's MEMOCODE. So once again, we have this strange setup where we are in hybrid mode, actually multiple hybrid mode. I don't know, is there anybody physically in Phoenix now, also at the ESWeek? No, I don't see any. Okay. So, well, glad that you all made it from different countries, different time zones. And so in this year's edition, we had 30 submissions, out of which 11 long presentations and 3 work in progress papers were accepted. And now it's my great pleasure to introduce our first keynote speaker. So it's Nan Guan from the City University of Hong Kong. And he is currently an associate professor there at the Department of Computer Science. And he obtained his PhD in Europe at Uppsala University, Sweden. And his research interests include real-time embedded systems, autonomous systems, cyber-physical systems, and the Internet of Things. And so today we are going to hear about robotics, as we will see in a moment. And so Nan received the ACM SIGBET Early Career Researcher Award in 2020, and the EDA Outstanding Dissertation Award in 2014, and a number of other awards. And he's currently the General Chair of RTAS 2022 and the Program Co-Chair of several venues. So I'll just mention the ISOR 2022 and RTAS 2021. And he is currently serving in the Execution Committee of the IEEE Technical Committee of Real-Time Systems. So today, Nan will give a presentation on the theory foundation for the real-time operating system, ROS, which I guess quite a few of you have already heard about. And so, Nan, the floor is all yours, please.
Okay, thank you. Thank you very much, Brennan, for the introduction. And also thanks, Jens, and all the organizers for putting together this nice event. And I'm very honored to introduce our recent work on real-time systems based on a robotic operating system. So just a few words at the beginning. So I want to apologize that during my break, actually there will be a 1 minute break, one minute interruption, because I'm staying in campus and it is a bit late in Hong Kong. So the university will ask people to leave the campus. So there will be a very loud broadcasting. So, but the good thing is it will speak in both Chinese and English, both Cantonese and Mandarin. So it's a good chance to see some diverse culture things. Okay. Yeah, don't be too surprised if you hear that. Okay, so yes, the focus of our recent work is on ROS. So what is ROS? I suppose probably most of you have heard of that or know them quite well. But anyway, so let me introduce very briefly. So ROS is a robotic operating system. And although it is called operating system, actually it is not a real operating system. It's actually a meta operating system or middleware. So it is installed on a real operating system, for example, Linux or other RTOS. And so basically, it provides a nice interface for the application developers to increase the software production efficiency. And ROS is, of course, open source. And so it has a very nice structure architecture based on the publish and subscribe communication paradigm. So this makes the overall architecture has very good modularity. So it is very easy to decompose the system, to reuse the existing components, and therefore it is very friendly to non-experts. For non-experts, I mean not experts in computer science, but they are domain experts in, for example, robotics. So they can just write their own algorithm, and that can be very easily integrated into any other projects. So it is very nice, very popular framework for robotic software development today. Probably like people consider this is the most promising framework. So yeah, here I give a picture about the architecture of ROS. So we can see it's sitting here in between the application and the operating system, and there are libraries and there are communication middleware which is based on DDS, at least for the latest version, and a lot of other things. Probably later I will mention some of them if needed. So ROS is actually, of course, it's a middleware, but it is interesting not only because it is a useful middleware. It is interesting because it has a very nice ecosystem. Okay, so like some people define ROS as the plumbing, plum tools, plum capabilities, plum ecosystem. I don't know if this is a perfect definition, but at least this gives you some kind of intuition. And if you want to check the ecosystem of ROS, it's actually a very rich. So you can find a lot of tools, a lot of libraries, simulation environments. So you can do things very easily with it. And it is very friendly for beginners. So they prepare a lot of patches. They put things in like containers, for example, that you can easily use. And it has been used in a lot of realistic robotics. So here I just steal some pictures and some names from internet. I think there are actually a lot more than this. And also, yeah, here there are some numbers. I guess I don't need to repeat. So there are a lot of like very encouraging numbers that if you see it, you will have a feeling, very general feeling that ROS is actually a very promising. And another reason for us to be interested in ROS or the real-time aspect of ROS is because like recently we have some projects on autonomous driving, right? So autonomous driving is very popular today. I guess many people has more or less some work related to autonomous driving somehow. Okay, so we also have some work to do with that. And in particular, we built some system based on AutoWare. AutoWare Foundation is open source framework, one stack software framework for autonomous driving systems. So they provide easily to use and rich libraries to build your own autonomous driving systems. And so AutoWare is also built on ROS. So these are two very closely integrated ecosystem. So therefore, in order to make autonomous driving system based on AutoWare to work well in reality, we have to solve their real-time capability problems. And of course, we have to look into the ROS layer, right? And also, last year, there was a panel discussion in RTAS 2020. And so we invite several people from both industry and academia. So they all work on different types of autonomous machines, in particular autonomous vehicles, and to discuss. So is there like possible to have something analog to the Android in the mobile system domain for robotics? Okay, so does it make sense? And is it possible? And if it's possible, then what it could be? So this is, I think, it's very interesting discussion. The idea is, robotics, different systems are very different, but they share some similarities. So if there is like a dominating platform, then it is very good for both the ecosystem and also for research, because for research people we have a more concrete target to look at. All right, so far these are just some very general information about ROS. So I try to motivate a little bit. So why do we work on ROS? So even if ROS probably from the real-time capability point of view may not be the perfect solution, but I think if it is the thing that is used in reality, and we have to live with it, right? It's like many people complain Linux is not perfect operating system, but people have to use it anyway, right? Okay, so then just start to talk about the real-time capability of ROS. so this is important, of course, because not only for autonomous vehicles, actually for a lot of robotic systems, the real-time capability is needed because they have to meet certain real-time constraints, right? So because the robotics has to match the inherent dynamics of the physical environment or the physical objects. Okay, so real-time requirement is really a nature in robotic systems. But unfortunately, the first generation of ROS, like ROS has like almost like 10 years and a bit more than that history. And the first generation of ROS was not really real-time friendly. So because the main philosophy behind ROS is to provide good modularity. Okay, is to really provide very high development productivity. Okay, so and it's always a trade-off, right? So I think at the very beginning, probably the real-time capability is not taken into the first order consideration in architecture design. So it has a lot of issues. And actually, about 5 or even 6 years ago, I already looked into the ROS because I think this is very important software, and I try to like work on the real-time aspect. But back to that point, I was very disappointed because I realized it is impossible to do anything with ROS for real-time capability because like we don't really have a very good foundation from the system point of view. But the good news is from about 4 or 5 years ago, ROS refactor its architecture and provide ROS2, the second generation. So the second generation has a lot of difference from the first generation. And one of the most important differences, ROS2 improves a lot in terms of the real-time capability. Okay, so if we want to like very briefly compare the ROS1 and the ROS2, so there are like several key differences. First, as we can see here, ROS1 can only be installed on Linux, but ROS2 can run on also other operating system, like conceptually on any operating system. Okay, it is not tightly coupled to Linux any longer. And a second, so ROS1 used the TCP and UDP for communication directly, but actually ROS2 used DDS. Communication middleware, which has a better real-time capability. Of course, like people can still say DDS is not like real hard real-time. It still is only can like support a very limited real-time capability, but actually it is already much better. And also, like there are some other features. For example, ROS2 doesn't have the master, doesn't have the central node, so it doesn't have the single point of failure, which is good for both the reliability but also for the real-time capability somehow. Okay, so there are a lot of things about the ROS2 and it's a system aspect. But here, I guess I don't have to really mention everything. So there is a real-time working group in the ROS development community. So there's this group takes charge of the real-time features of ROS2. So they are currently, they have been and currently are very actively working on a lot of projects, topics to continue to improve the real-time performance of ROS in many aspects. So all these aspects are on the system level. So they try to make the code, for example, like the critical code path shorter, right? So we have a much better responsiveness and something like this. Okay, so these are from the system point of view, system perspective. So ROS2 already has a decent foundation for building some real-time systems. And hopefully in the future, it will become even stronger for real-time performance. So this gives us the opportunity to really seriously consider apply ROS to the like realistic robotics with real-time constraints. And yes, of course, so we are sort of the academia people, so we don't really work on the same thing as the ROS developed community. So our perspective is to work on more theoretical aspect for contributing to a better real-time robotic operating system. And so the first thing that we can do and we want to do is we certainly can analyze the real-time performance of the applications developed on top of ROS. Okay, so for example, we can model the applications developed on ROS. As I said, the ROS has a very nice architecture where the applications has like very decoupled architecture. So it is very easy to model the ROS application because they basically just publish and subscribe message from each other to exchange data. Okay, so we can model the application, for example, with some graph interface, and we can provide some automatic analysis tools. And for example, to check whether the deadlines are always honored. And this is useful for developing hard real-time applications, because for hard real-time application, we have to check, we have to provide this kind of guarantee, either strong or weak, but it is important. Actually, this is also important or meaningful for soft real-time applications where we don't really, I mean, missing a deadline does not necessarily mean anything like so serious, but still we want to optimize their performance as much as possible. And if we have some kind of analytical tools that it is easy to identify the performance bottleneck, the real-time performance bottleneck, therefore to improve the system in a very efficient way. And we also would like to do a bit more than just analyzing the applications on existing ROS. We also want to discuss like how the ROS architecture should evolve in the future. Okay, so we have some like exchange with the ROS development community, especially the real-time working group. And they have a lot of brilliant ideas, but at the same time, we can feel that they also have a lot of question marks because, I mean, designing a system is not, sometimes it's not only about what is better than the other, but it's also about the trade-off between the consideration from different aspects, right? So they also want to understand what would be the most important or the critical bottleneck currently existing in the current version of ROS, and does it work to really change anything to make it better? What would be the gain from the real-time perspective by doing this, like this kind of question? So if we can, of course, people can do a lot of applications and can do a lot of experiments to provide information, but if we can give some more analytical insight, probably this is also useful to get the involvement of the ROS architecture. Okay, so this is basically the big motivation behind our recent work on this topic. Okay, so in the following, I will introduce, I try to categorize our work or our thinking in three categories. On the timing predictability, so basically it's the technique about how to model and predict the real-time performance for the applications like developed on ROS. And the second, the timing determinism. Okay, so timing determinism is determinism is a good thing for real-time system, right? So the question is, I mean, for ROS, is it really deterministic or not, or can we do anything to make it more deterministic? And the third one is timing robustness. So I mean, for a lot of realistic application, so there are a lot of unexpected disturbance. Even if you have a very nice model, but in reality, things may go differently. So in that case, how can we like sort of tolerate this kind of disturbance in reality? So this is another topic. I guess most of my time will focus on the first and also the second topic. And if I have time left, I could say a few words on the third topic, because we don't have so much insight yet. We just have some very preliminary thinking. Okay, so the first aspect, the timing predictability. So this is actually sort of the comfort zone of our research group, because in the past we have been working on modeling the real-time systems. So we have a like very abstract model, for example, a system that is modeled as a DAG, okay, and we assume some parameters are known, and we assume this is a closely well-defined system. Then we start to develop some mathematical relationship between the parameters and its real-time performance, and we want to check if this is satisfied. So, and we want to do something similar with the applications developed on ROS. Okay, and in order to do this, then we have to understand what are the important features of ROS that like affecting, influencing the timing behavior of the application, right? So if we want to, for example, if we want to model application running on some operating system, probably we need to understand what is the scheduling policy of the operating system, right? So for ROS, this is similar. There are certain components which plays very important role on this. And in particular, we, at least so far, we have looked into two important components. One is called executor and another is called message synchronizer. And in the following, I will briefly introduce what are they and what did we do with them. And actually, we think there are a lot of work to be done yet. And we also are aware of a lot of recent work, not from our group, from many other groups, and we see more and more work have a deeper and deeper discussion with similar topics. Okay, so the first one is executor. So what is executor? So for those who don't know this, I just briefly explain this. So in ROS, so this is the logical view of application. Basically, the application is just a collection of nodes, right? So like different people can develop their own node. And the node, basically, you can consider node is just a class in the programming language, right? And in the node, there are a lot of callbacks. You can just consider them similar to be the method in the class. Okay, so you can write your own class, can do certain work. And different people can just reuse your node. And those callbacks are the like sort of the task or the codes doing the job, right? And these callbacks will be mapped into something called executor in ROS2. They will be registered into the executor. And the executor will coordinate the execution of different callbacks, because we may have a lot of callbacks like executing concurrently, like we have multitasking in operating system, right? So different callbacks exchange information with each other by publishing some message to some topic or subscribing some message from some topic, right? So this is very simple, very elegant paradigm. Because the executor, okay, because the executor coordinates the execution of different callbacks, so there should be some order to execute them, right? So who execute first, and if some callback have to be executed for multiple times, like how often or in what time of occasion should be executed, right? So this is basically the role of the executor. Then this is apparent executor plays a very important role in the timing behavior. So basically we can say the executor is just playing a similar role as the scheduler in operating system. Okay, so so then what are interesting things about this? So when we start to look at this, before talking about the ROS executor, I just mention another thing called round-robin scheduling. Okay, so I guess the people all know what is round-robin. Basically, you have multiple like participants, and every participant wants to do some work. Then you do the work in rounds. Each round, like each people just do one piece of work, for example, or there may be other variants, but let's just consider the simple version. And if in the current round, some participant doesn't have any work to do, then it just does nothing in this round. In the next round, maybe it has some work to do. Okay, so this is the basic principle of the round robin. Okay, and the participants can do this work in some predefined order. And round robin has been widely used and has been very well understood. There are plenty of analysis techniques to, for example, analyze if you have multiple tasks are scheduled by the round robin, and how to, for example, calculate the worst case delay or end-to-end delay or something like this. But in ROS2 executor, they use something which is very similar to round robin, but slightly different. And we call it lazy round robin. We just give this a name. I don't know if this is a best name, but we call it lazy round robin. So why I call it lazy round? Because it is very lazy. Because during the round, it doesn't really check any newly arrival events. So in the traditional round robin, so during the round, okay, so at the beginning of some round, some participant doesn't have any work to do. But in the middle, like some external event happens and this participant has something to do, then immediately this will be taken into account. And if it's currently the turn of this participant, then this newly arrived workload will be executed. Okay, but in lazy round robin, in ROS2, it doesn't check this. Okay, at the beginning, it already decided in this round what will be executed. And in the middle, if something happens, we just ignore it. And we postpone like handling or recording all this external event until the beginning of the next round. Okay, so this is a small difference between the round robin and the lazy round robin. So as the example we can see here. Okay, so here suppose at the very beginning only task 1 and task 2 has work to do, but at some later point task 3 also has work to do. Then we can see in traditional round robin, like task 3 will also do this work. But in lazy round robin, okay, so in the first round it will be ignored because everything is already decided at the very beginning. And in the second round, this arrived event will be considered. Okay, and so on. So this is a very small difference. And of course, so because there's a difference, then we have to analyze the new behavior, right? And we not only analyze the new behavior, we also want to understand what difference does it make by introduce this very small difference into the ROS executor. Is it much better or much worse? And if it's much worse, then can we quantify how worse is it? Something like this. We do some like theoretical work. But actually, another interesting question apart from analyzing what is there in ROS2 executor, we also ask why does ROS2 executor use this lazy round robin at the first place? By the way, so our conclusion is a lazy round robin is much worse than round robin. Round robin is already very simple and not really real-time friendly, but lazy round robin is even worse. And intuitively, this is easy to understand because you artificially ignore some event may be urgent. Okay, so of course it's much worse, and we can quantify how worse is it. But the question is why, like, do we have to live with this, right? Is it a big reason that we have to live with this? Actually, there's a reason. This is because, as we said, so ROS used this very elegant subscription, publish and subscription communication paradigm based on the DDS communication middleware. So these two parts, the executor and the communication middleware, they are very decoupled. So they are like very two different things. They work in different processes. They have they could be even totally isolated. So the information exchange between these two components is very expensive. So this is the reason that we cannot afford to, like in the round robin, to immediately respond or actually to check what is the new thing coming from the DDS, because we always have to ask DDS, is there anything new, right? We have to define some particular point to ask DDS if there's anything, okay? And because of this expensive overhead, this is the reason why ROS2 choose to use this lazy round robin, but not ordinary round robin, okay? So then we figure out this is the reason. Then we start to discuss, okay, so if this is the reason, can we like develop some other scheduling policy which may have similar average overhead, which means we don't ask the DDS so frequently, similar to what is currently in ROS 2. But on the other hand, we try to be a bit more responsive in the presence of urgent event. So can we redefine the opportunity, the timing for asking the DDS and make the real-time capability much better. So then looking into this kind of question is also quite interesting. It's also part of work. Here, just try to give you some sense what are we doing here. And we not only look into like a small component or a particular component. Of course, we want to understand for the whole application based on such a component, what would be the timing behavior. And usually the ROS applications can be modeled as a processing pipeline or a processing graph. Basically, you have some sensing data like flow into the system, and you have different algorithms to process. For example, here, this is a autonomous driving system, which is very abstract, but you can see like the sensor data flows into the system and go with a very deep pipeline until you reach the end. Therefore, we have to model the systems. We have to model the system with like this system level models and do the system level end-to-end performance analysis. And also for the executor, there are also some other details, and because the ROS2 executor may use, for example, only one thread to execute all the workload, or it can use a lot of threads at the same time. Okay, and if they use a lot of threads at the same time, then there could be some other constraint imposed on these threads. Okay, so without really talking about all these details, I mean, just here give you some idea that actually there are a lot of possibilities, like for the application, like how to use the basic facilities provided by ROS. Okay, so then we can do this kind of analysis. Okay, just give you some example. So for example, this is one of our paper's result. So if we consider a processing chain, then if we put it into a single thread executor, then some interesting property has been reviewed. So for example, we can see that actually the different priority assignment of different callbacks doesn't really change the behavior of the scheduling in the process. We don't know what is processing window, but it doesn't matter. Okay, so basically it doesn't change too much of the timing behavior. Okay, so this is interesting. Like no matter how do you assign these properties, a lot of things doesn't change. But the priority assignment indeed changed something, because if it only depends on the sync callback, which means if you have a chain, then the timing behavior of the whole chain only depends on the priority of the last callback in this chain. Okay, so this is also very interesting, because before that people didn't know this. Then in order to improve the real-time performance, probably they tune the priority of all these callbacks. But here, like there are evidence showing you don't have to do this. Probably you only need to tune the priority of the last callback, something like this. Okay, so this kind of property hopefully could be useful not only for analyzing the system, but also guiding how people design the system. Okay, so I think I just stop here with the executor. And next, I will talk about another component that we look into, which is called the message synchronizer. This is another interesting component in ROS. So what is the message synchronizer? So in a lot of robotic systems, there are sensor fusion components that fuse different sensors. For example, in autonomous vehicles, usually we will do fusion for the camera data and the LiDAR data in order to better perceive the surrounding environment. Okay, so we put different types of sensors and put them into the same algorithm. So you can see, so these two information flow will meet each other in this component. And when they meet each other, functional, like from the functional aspect, this is pretty clear, but from the timing aspect, there are some details we need to take care of, because different sensors that do not necessarily provide the data at the same time. For example, they may have different like sampling frequencies. Some sensor may working faster than the other. And also, not only their frequency for producing the sensor data could be different. Even if two sensor data are produced exactly at the same time, because before reaching the point that they meet each other, they may have to go through some processing pipeline already, and there may be some delay, and the delay could be different. Okay, so like the different data may arrive the synchronizer at different time point. Okay, then the role of the message synchronizer is to waiting for the sensor data from different streams arrive and try to find the correct pair or group among them. Okay, so intuitively, you always want to put in those sensor data with the same time step together, right? You don't want to fuse the camera data with the LiDAR data, which happens, for example, 1 minute ago, right? Because it doesn't make any sense. It doesn't provide you any useful information. So you always want to try to find those data that are produced at the same time. All right. So this seems to be a very easy task because you just look at the time step, then you just pick them with the same time step and put them together, and that's it, right? So this sounds quite simple. But in reality, this is not necessarily true, because if you don't pay enough attention and use some simple policy, then it may lead to poor temporal consistency. For example, there's another framework used a lot for autonomous driving system, which is called Apollo Cyber RT, which is like playing similar role as ROS, but it is different. So there they use a very simple policy. So basically, they always pick the latest sensor data from each data stream and put them together to match, right? So they always use the latest data. Then, of course, there will be a problem because, as I said, different data may experience unbalanced delays. For example, some sensor data may experience a much longer delay before reaching the fusion point than the other one. So this delay takes 60 milliseconds, the other delay takes 10 milliseconds. Then if you look at what happens in reality, then you will see, according to the Apollo Cyber RT's policy, then it will choose these two sensor data into one pair, feed into the fusion algorithm, and put these two into the fusion algorithm. Then you can see there's a significant difference between their time step, which means like the fusion algorithm is a fusing like information happened at significantly different time. Then this may give you a wrong result, like logically wrong result, right? So this is something we have to solve. Then, of course, people may come up with some ideas, say, okay, we can do this a bit more carefully, then we can then find much better matching, right? It turns out this is not really a trivial task. Actually, ROS really did a lot of work to solve this problem. ROS provides this message synchronizer component exactly for this purpose. And as you can see, actually, this component is fairly complex in ROS. It has like around 1,000 lines of C++ code. So you can imagine there's a lot of checkings and calculations to decide which one to match which one, to consider all the possible corner cases. Okay. And so if this component is so complex, I guess for most application developer, they don't have the capability to understand what are they doing exactly. Even if like functionally you can read the code, I guess it is not so apparent to you for your application what would be the consequence of using this. Okay, so if your application has some particular timing behavior and under this particular policy, then what would be the sequence? Will this be always consistent, or there will be also some corner case at some point, some sensor data which has a very large distance from in their time step will be put together and produce the wrong result. Okay, so I think this is some question the application developer don't have the capability to answer. Okay, and in our work, we formally model the behavior of this component and do the analysis, and we mathematically prove they're actually very like simple upper bound for you to bound. Okay, what is the maximal distance of any pair of data that you put together by this synchronizer, then feed into the fusion component according to the parameters of your sensor data. Okay, so of course, if some of your sensor data has a super large period, some has a very like small period. In some very extreme case, and the delay are very different. In some extreme case, you may have some problem, but in general, so this is not very huge gap. Okay, so it's a pretty reasonable upper bound, and we can prove this upper bound so people can use it safely. And behind all this work, another important question is where does this model come from? So we claim, like we do theoretical analysis for ROS, right? We claim we understand the behavior of ROS, and all of our theoretical work are conducted on some model. We need some model, therefore we can do some math, right? And if we are given a well-defined, well-described model, then we can start to work with it. But the problem is where does this model come from? This is actually even a larger challenge that we face in doing all this kind of work. And until today, we don't have a perfect solution for this. So we always has to face the challenge that people say, okay, yeah, you claim you understand it, but probably your understanding is not correct. So your result is useless. So we always face this kind of question, and we don't have a perfect answer to this. And so here I just report what we are doing, and hopefully if there are some good suggestions that we can look into, then I will be more than happy. So basically the best that we can do is we just very carefully read the source code, right? We just have to manually use our brain, try to understand what is the logic behind. And after reading the source code for like a period of time, and so we sort of we believe we understand what is the behavior, and we try to exclude those aspects which are irrelevant from the analysis problem that we are doing. Okay, so we sort of extract a pseudocode. Okay, we only look at those code that are relevant to our problem, and also try to make the code a bit more abstract, a bit simple. And based on the pseudocode, then we do some refinement. We do some further refinement. Okay, so this refinement, we need a lot of proofs. So here we also do a lot of refinement. We just get rid of some code, which is at the first look you already see this is irrelevant from for the timing behavior, because it's computing something else. Okay, and there are a lot of more tricky cases. Okay, so there are some, for example, there are some optimization, there are some particular algorithm ordering those data frames in some way, and if you take this into the model, then your model have this ordering algorithm which is so complex. But if you, okay, so I don't know if you can hear this, but
the university campus will be closed.
Okay, yeah, I guess I just keep talking anyway. Okay, so if you want to get rid of all these details, probably the timing behavior is different. Okay, so for this kind of more tricky details, then we have to sort of prove them. We start to formulate smaller problems to prove locally, getting rid of all these details. For example, this particular optimization algorithm, we can just remove it from our abstract model, because with it or without it, the timing behavior will be the same. We have to formulate some small problem that we prove. And if we manage to get a very short, very simple refinement of the pseudocode, then we can make a model in the way that we can write into the paper, right? We can draw the picture, then the reviewer can understand. And finally, we can do the proof. The final step is the thing we are really good at. But for everything before that, actually, we are not so sure what we are doing, right? We are not so sure if we are doing the best thing. And of course, we need some validation. We need to validate at least the refined code that is the same as the source code. Therefore, we did a lot of validation. After getting rid of all these obvious details and less obvious details, we write a much simplified version without any optimization, just in the very simple way. And we try to make our confidence as high as possible with those code. And we run these two algorithms concurrently in the same system, always receiving the same input and at the same time, and do the decision at the same time, and synchronize at some point and produce the output. And we compare if their behavior are exactly the same. And we have run this kind of experience for like days and weeks and for particular settings. And sometimes we find some bug and we come back to our model and we have to revise them. And after a while, because we don't really see any bug and we don't know where to improve, and we sort of claim this is the understanding that we have. Okay, so but again, this is obviously not a perfect answer, and I would like to get feedback from you guys. How can we do this better? Okay, the next topic, I guess I don't have much time. Let me speed up. The next aspect is timing determinism. So what is the timing determinism? So we want to make it more deterministic for the timing behavior. So this is useful for the critical systems, right? Because this can make your system behavior much more simplified, right? So then you can, it's much easier to provide timing guarantees, right? For example, if we use time trigger execution, then probably it's a lot easier to make your system correct in timing. And this kind of timing determinism is also useful for those systems which are not so critical. Okay. The reason is one of the reasons many people like ROS, because ROS provide a very nice simulation environment. So you can easily build a simulation environment and to simulate your software. Okay. But obviously, there's a difference between the simulation and the real implementation, because your simulation code, when you put it into the embedded device or the real robotic, then probably there are a lot of differences. Okay, so like certain types of determinism can guarantee that a lot of things are independent from the implementation details. Okay, so no matter how long is the execution time of this particular piece of algorithm, okay, so your algorithm always produce the same result, at least logically the same result, then this is a nice property, because then what you have validated or verified with simulation can be carried into implementation. Okay, so this is also a nice property, but only if we can provide such a timing determinism. Okay, so if a little bit like timing changes in reality and all the results could be different, then we cannot really do this. Okay, so for the determinism, this can be done on the component level. For example, again, I take this message filter as an example. Okay, so as I said, so each data frame may experience some non-deterministic delay before arriving the data fusion component. Then the question is, if this delay changes a little bit or changes a lot, in any case, will the synchronization component pair them differently? Therefore, they will produce like different results. Is that the case? So here, let me just explain again. So even if, I mean, for the timing that produced the data frame, that are exactly the same, but the time arrive this time synchronizer could be different. So if they arrive at different time, then the synchronizer at some point may have to take some different guys from each stream and put them into the same group, right? So then this creates some kind of non-determinism. Then after some investigation, we can prove that actually this is not the case. So the message synchronizer in ROS have some nice property. Okay, so the delay change does not change anything from the logical point of view to your output. So this is nice. Actually, this is not the like we are not the first one to claim this. the developer of this algorithm in ROS development community already claimed this property, but they didn't provide any formal like proof. They didn't prove this. They just claim this, and people buy this. But we can prove this. And more importantly, we realize this is not always the case. Okay, what they claim is true, but only under certain conditions. And these conditions are usually like reasonable, but I mean, this is not always the case. Okay, so then we sort of raise the alarm, tell people, okay, so they are right, but not always the case. Okay, so we can identify some case that this is not the case. And the determinism can also be on the system level. Okay, so and usually, so we want to make the whole system to be more deterministic, for example, by posing more restrictions. For example, if we let the entire system to execute in a time-triggered way, then it is obviously more deterministic. But unfortunately, ROS very unlikely accept this kind of strict execution paradigms, because ROS is a very general framework and it serves for general purpose. Different people use it for different purposes. You cannot really make it too restricted, too difficult to use, or sacrifice too much general performance. This may not be useful. So ROS will never accept a time-triggered execution pattern. This is my guess. Okay, I may be wrong, but this is my impression. So then our target is to develop a less restricted execution paradigm that can also provide on one hand, it can capture the essential features of ROS. In other words, it can be relatively easier for ROS community to accept, and on the other hand, does not provide pose overly strict restrictions to the behaviors and offers like certain determinism. Okay, so I guess let me okay, so I think okay, so for the timing determinism, so we try to like look into a bit what does it mean by timing determinism exactly. Okay, so people use these words, but probably for different meanings. So we consider this into two cases. One is the strong timing determinism, which means okay, so given different input, okay, so the timing behavior is determined by the like a different input. Okay, so in other words, for example, for the time-triggered execution, okay, so for the time-triggered execution, so if you can keep the input always the same, then you always produce the same result. Okay, and the weak timing determinism is the timing of the outputs produced by the system is always the same. It's always the same, given the same input, Okay, in the sense of both the logical value and the timing point of view. That means sometimes we don't want the timing behavior of the entire application to be exactly the same if you change something. But what we want to guarantee is your logical result is always the same. Then this could be also useful in a lot of cases. Then we try to did some investigations, and I have to speed up a little bit. So we look back into the history, and we find some recent paper from, actually this is my PhD supervisor, and he invents some new model which is called the timed version of the KPN, which is has some nice property. Okay, so this timed version of the KPN is basically introducing the timing concept of the into the KPN, okay, and captures the essential execution and communication paradigm of ROS, and provide both the function and the timing determinism in the weak sense. Okay, and without talking about too much detail, I will stop here, and finally just a few words about the timing robustness. So in the ideal world, so we always want to do the analysis, rigorous modeling analysis for the system, and we want to try to prove the system is correct. Okay, but this is not always possible because we have to face the software and hardware complexity. And actually, this is the challenge, like an even bigger challenge that a lot of people face in this community. Okay, so we are not, especially a lot of robotic applications, they are super complex. We don't have the capability to provide even a simplified version of the model. Okay, so, and on the other hand, in many robotic applications, the hard real-time guarantee may not be required at the first place. Okay, so then probably making this kind of rigorous modeling analysis is anyway like over design. Okay, it's overkill. So then the target is can we maintain the correct timing behavior as much as possible, and in the presence of the unexpected disturbance. This disturbance could be because of the external source, or for example, some interrupt that you are not aware of, some external event that happens unexpectedly, or some internal factors. For example, maybe you don't have the capability to very precisely bound the W set of some component, something like this. A lot of different factors. Okay. And so then, like one possible way that we are thinking of is we want to provide a capability in ROS to do some automatic model construction. Okay, so we just let people run their application. They don't have to draw any figure, do any modeling. They just run their application. Then we can collect a lot of trees based on their execution. And we can use these trees at the runtime, sort of make some model. This model may not be a complete description of the system, but at least it captures some typical behavior of the system anyway. Okay. Then we can already do some analysis based on this model, and also using this model to give us some useful guidance. So we can do some runtime monitoring of the progress of the execution of your application. Okay, so for example, we can capture the timing of some key events and so on. Okay, and the key point is because we already have some structured information of your application, and we can monitor a lot of information at the runtime, then we probably can predict some like bad behavior would happen in the future, and to adaptively do the scheduling and then dynamically adjust the resource allocation to, for example, give the more urgent tasks higher priority and like suspend those less important. Basically, this is the what people call the mixed criticality scheduling, right? But we just put it in a more concrete context. Okay, I think I'm running out of time, so I think I just summarize. So like we are working on ROS, and real time is important for ROS, and we want to work on more serial aspect of ROS, and we are at the very beginning, and we have to do a lot in the future. Okay, yeah, thank you very much, and I would like to take questions if there are any.
Okay, yes, thank you very much, Nan. So yes, very inspiring, especially personally, I found the second half, the determinism, very inspiring. And I have a couple of questions, but first, so I think maybe there would be one question that we could take from the audience. I would be happy to delay mine if there's any question. No. Okay. Well, then maybe briefly, if you could go back to slide 22, maybe. So I understand that your effort is also about about extracting a model of the timing behavior and then analyzing that timing behavior, right?
Yes.
Yeah, and so I'm wondering, since you also mentioned architectures like time-triggered execution and so on, so there at least the classic approach would be rather the other way around, to start from a model and then to refine that model with an implementation and so on. So would you see any room for that kind of approach here in this context as well?
Okay, yeah, I think this is a good question, because I mean, what we are doing here actually, we are aiming at this kind of model-based design. So we hope to do this, so if we can start with a model and with some like execution, like certain properties, then we can like make the implementation to be synthesis. But on the other hand, we have to live with all these features. Like if we want to run on ROS, if we don't want to use ROS, then that's another story, right? If we want to use ROS, then we have to face all this. Then the question is what is the meeting point? And we try to understand this, right? So I mean, for example, if your scheduler is not time triggered, then probably you cannot assume a time triggered model at the first place, right? Probably if it's a priority driven, then probably you can assume a priority driven model or something like this. Okay, so I guess I think I agree with you. All this work we are doing is it's sort of what we are like looking from the source code and extract the model. But this is actually not the case because we are not looking into the application source code. Okay, we are looking at the infrastructure, the middleware, the operating system source code, and to extract this and to make our model sound. And for the application, we hope we can start with the model and do the like a top-down design.
Okay. Okay, great. Thank you. Well, I think I would take my other questions offline in the interest of time. So yes, thanks again for your presentation.
Okay, thank you. Thank you very much.
Okay, so and with that, I would like to hand over to the next session chair. So then would Lee Jun, would you like to take over?
Oh, yes, thanks. So we have the first session of our conference. I see that we have both speakers in the list. So the first talk will be given by Anup. So Anup, could you see whether you can share your slides?
Absolutely.
Great. So the talk is about real-time scheduling of machine learning operation on heterogeneous neuromorphic SoC. So please go ahead.
Thank you. You can hear me okay? And can see me as well. Okay, great. Excellent. So hello, everyone. My name is Anup Das, and I'm an associate professor at Drexel University. I direct the Distributed Intelligent and Scalable Computing Lab at Drexel. And today I'm going to present our work on real-time scheduling of machine learning operations on a heterogeneous neuromorphic SoC. So I'll start by giving a quick summary of the work. Basically, neuromorphic computing are everywhere, and you have already seen quite some improvements achieved by neuromorphic computing, specifically using non-volatile memories and so on and so forth. It can achieve a really low energy consumption in machine learning operations. And that is what makes it a very attractive solution for edge devices where the power is limited. We all know that technology scaling has brought quite some advantages, and those advantages have also brought down the power consumption of neuromorphic computing quite heavily. Neuromorphic hardware platforms are now integrated with other system components like CPUs, GPUs to form a system on chip. And we'll refer to this as a NSOC throughout my talk. However, existing system softwares are not fully developed to handle this system on chip complexity. Specifically, we'll see that these softwares cannot exploit all forms of parallelism that an NSOC offers. Moreover, they can only schedule one application at a time. As we'll see later in my talk, there will be situations where a platform may need to execute more than one machine learning applications at the same time. And such scenarios cannot be handled using the existing software. So in this paper, what we did is we proposed a scheduler called Prism, which is for real-time systems, and it utilizes all the system components to enable three forms of parallelism, which are batch, pipeline, and operation. We'll discuss what these are later in my talk. Now, Prism is also able to schedule more than one application at the same time. Using 20 workloads, we show that Prism improves throughput by 20%, throughput per watt by 38%, and also has a much shorter wait time to generate a schedule and begin executing an application. So this is the outline of today's talk. After the introduction and the platform description, I will introduce Prism and then present the evaluation and finally the conclusion. So I'll start with a quick introduction to neuromorphic computing. Spiking neural networks are what neuromorphic computing are meant for. They enable powerful computations, mostly due to their spatiotemporal information encoding capabilities. And SNNs are implemented on a many-core system, which you can see towards the right. Now, often machine learning models are large and they cannot fit onto a single NPU or a single core, and therefore the model usually is first clustered and then the clustered models are mapped into the cores. A few key differences between spiking neural networks and the conventional ANNs, example, a convolution neural network, is that a spiking neural network communication happens via spikes, and the computing units are some variant of integrate and fire neurons. So we'll mostly focus on the inference engine. That means you have a model which is already trained, and how are you scheduling that trained model onto the hardware resources. So we'll now explain the NSOC platform and present the motivation of this work. Now, an NSOC, which is shown on the right, consists of CPUs and neuromorphic hardware. A machine learning model can be executed either on the CPU, in which case synaptic weights are typically stored in the main memory. However, this is not the most efficient way of computing, as we all know. And this is primarily because there is a limited memory bandwidth. So moving the large amount of weights or parameters from the memory to the CPU to do the computations becomes a challenge, which is also why CPUs are more energy consuming as compared to a neuromorphic hardware. Now, when a model is executed on a neuromorphic hardware, computations become more energy efficient. And this is primarily because when you think of a single neuromorphic processing unit or NPU, it can integrate the logic and the CPU inside. And therefore, there is no memory bandwidth bottleneck come into play. Now, once computations are offloaded to a NPU, it can work relatively independently of the CPU and can perform its computations and then communicate them to other NPU where other operations may be mapped. Now, typically a neuromorphic hardware also consists of a scratchpad where all these intermediate computations may be stored before they are handed over to the next NPU where the computations continue. Now, a NSOC may be integrated in an embedded platform to process audio and video data. Typically, what happens is the data is first streamed into a buffer, and from that buffer, the data is partitioned into mini batches, and each mini batch is then scheduled on a NPU of the hardware. And typically, number of mini batches that are formed is equal to the number of NPUs. In this way, multiple mini batches can be executed in parallel. Now, a system software for these systems usually consists of compilers and schedulers, and they coordinate the machine learning model execution on the hardware. So in this slide, what I'm showing is some of the common neuromorphic hardware that are available and their configurations, along with the system software that are used to map a machine learning model to those kind of hardware. Now, a key limitation of existing software is that it can run a machine learning model only using the NPUs of the system, which essentially means that very rarely you will see a system software that make use of both CPU and NPU or other computing resources of the NSOC. Now, why it is important? If we look at some of the typical models that mobile or embedded platforms execute, you'll see that not all the operations of those models can be executed on an NPU. So here in this plot, what we are showing is the fraction of operations that are not supported on existing neuromorphic hardware platforms. And we show them for some of the evaluated models. Now, to give a few examples, if you see SqueezeNet can be supported on all platforms because its operations are supported on all of them. However, MobileNet can be supported only on one of the hardware, which is the spec hardware, and but not on all the other hardware. Now, finally, if you have to design a custom model, and remember, when you are designing a custom machine learning model, you are using the Lambda layer of your TensorFlow or Keras library, but however, Lambda layers cannot be supported on any of the hardware. And we all know that machine learning models evolve faster than hardware. So there is a clear need to support emerging models onto the existing hardware. Now, coming back to the parallelism that a neuromorphic or a neuromorphic system on chip can offer, we see that there are three forms of parallelism. A pipeline parallelism where processing of operations of subsequent input data can be overlapped in time. It supports operation parallelism where independent operations acting on the same input data can be scheduled concurrently. And batch parallelism, where the idea is to process multiple mini batches concurrently. And as I just mentioned in the previous slide, that most scheduler that you will see can exploit batch parallelism very well. That means all the different mini batches can be executed in parallel. Finally, if you see, embedded platforms may need to execute multiple applications concurrently. Now, imagine how often we listen to music while browsing on the social media. Right? Here, audio and video-based machine learning applications are happening all in parallel, and they need to be executed on the neuromorphic hardware. Otherwise, you will not get the proper advantage of a neuromorphic system for your platform. Now, existing scheduler cannot execute more than one application simultaneously, which is a big limitation. So with these limitations, let me now introduce you to PRISM. And PRISM stands for a performance-oriented real-time scheduler for machine learning operations on a heterogeneous NSOC. Now, PRISM works in 4 steps, which we are going to describe in the next few slides. So in step 1, what PRISM does is it creates a interprocessor communication graph from a model description. And you can provide these model descriptions using a H5 or a JSON format. And also it takes a mapping of operations to the processing code. Now, IPC or the interprocessor communication graph consists of 2 types of actors. They can have a communication actors or computing actors, where the actors that can perform operations, and these operations could be convolution, pooling, batch normalization, and so on and so forth. And it can also have communication actor, where the actors that are communicating data between the computing actors. Now, I will explain these actors in more details in the next few slides with the proper example. So we'll start with a simple example of a Inception block. And as you can see in this block, there are 6 convolution operations, 1 pooling, 1 input, and 1 concatenation block. Okay, so all these are the computing actors of the graph. Next, what we consider is a mapping. Now, mapping involves, by mapping we mean how these actors are allocated to the different computing units. And as you can see, some of these actors are allocated to the CPUs, while other actors are allocated to the NPU of the hardware. Now, in the context of this work, mapping refers to which operations are mapped to which resources of the hardware, and scheduling refers to in which order operations that are mapped to a resource are executed. Now, later on, we'll explain how this different mapping can control the throughput using a design space exploration tool, but that's towards the later part of the PRISM description. So for now, let's start with the understanding of PRISM from a given mapping, where we are seeing that some of the operations like input, convolution 1, 4, and 3 are mapped to the general purpose processor 1, which could be a CPU. Convolution 2 and 5 are mapped to NPU 1, and pooling, convolution 6, and concat operations are mapped to NPU2. Okay. So from this description, first thing what we do is we create interprocessor channels, interprocessor communication channels using the mapping information, and which is shown to the right side. Now, these channels are basically those communication unit where the data flows from one computing unit to the other. And finally, we add the communication actor to this graph. Now, I'll explain a little bit on how communication actors are being inserted. So for every interprocessor communication channel, we create a source actor, which is indicated with the letter S, and a destination actor, which is indicated by the letter R. Okay. The source actor is placed after the computing actor that produces the data, and a destination actor is placed before the computing actor that consumes the data. So in this example, you can see that you have S1 and R1 connected because the input produces a data which first goes into the send actor, and then the corresponding destination actor is located on another resource, which is R1 NPU2, which is on the top right corner, and that is placed right before when the data is being consumed. So essentially what you do is from the computing actors, you create additional actors, which are also called the communication actor. And these actors are placed one for each interprocessor communication channel. Now note that if there is a data flow from one computing unit to another that are mapped to the same resource, we do not create any source or destination communication actors. So once this computing IPC graph is constructed, we move on to the step 2 of PRISM. And in the step 2, what we do is we embed the transaction order into for the communication actor. Now, if you remember, our hardware that we have we presented earlier, it had both CPUs and GPUs. And also there are certain mechanisms through which data can be transferred from one unit to another. For example, the DMA or the scratchpad that can be used to interface between the CPU and the hardware or the NPU. So imagine a case where one of the operation is mapped into a CPU. The data produced by that operation need to traverse to the NPU. So it will use the DMA engine to first go into the main memory, and from the main memory, it might be used by the scratchpad. Okay. So all these shared resources are being used for the communication actors to communicate data from one resource to another. Therefore, if we do not generate an exact order, that means exact way to schedule this communication actor, throughput cannot be guaranteed. The idea here is that what we do is we start from the IPC graph and we eliminate all the computing actors because we know the order of the computing actors. We are interested in creating the order for the communication actors. So what we do is we eliminate the computing actors and retain only the communication actor, as you can see on the screen towards the right. Then using a recursive algorithm, we eliminate the communication actor one by one by considering its maximum cycle mean. And the exact mathematics is provided in the paper, and how we transition from one step to another is also provided. The idea is that you consider the maximum cycle mean of all actors that do not have any incoming edge, and the one with the minimum maximum cycle mean we eliminate from the graph and then reiterate the whole process once again. So we eliminate the communication actor one by one from this graph, and this particular example shows how we go from iteration 1 to iteration 2 and so on and so forth. Eventually, the sequence of the deleted communication actors becomes the transaction order, which we then embed into the main graph, as you can see using the red dashed line. Now, once the final graph is ready, we can compute the maximum cycle mean, inverse of which will give us the throughput. Now, this completes our step 2. So we will now transition to step 3. In the step 3, if you recollect that we computed the throughput starting from a given mapping, and this is exactly where we pointed out that we will use some design space exploration to explore the mapping space itself. So now what we have done is we created an IPC graph, we embedded a transaction order to it, we computed the throughput from it, but all these are based on one mapping that we have provided initially. So the idea would be to explore the design space of mapping to obtain a mapping that gives the highest throughput. And that is done using a typically hill climbing heuristic, but you can also use any other heuristic in this process. And what we have done is we have provided the GitHub link, which you can see how the hill climbing heuristic is being processed. Basically, the idea is you start from initial mapping, perform some swaps and compute the throughput. You retain the best throughput and reiterate the process. And if you think that the algorithm is stuck in a local optimum point, you do some random perturbations to move the algorithm out of your local minimum space. Okay. So hill climbing is pretty well-known algorithm, so I will not go too much details about it. So that essentially computes the mapping space. And what we do is we next move on to the use case mapping step, the last step of the Prism. So what we do is we map different use case for concurrent applications. This is the high-level overview of the Prism for the use case mapping. So essentially what it does is it uses the hill climbing mapping exploration, which we just described, to compute the different mapping and their corresponding throughput. And it uses them to and store it in a particular database. Use case mapping happens when it explores this database to find a case for mapping the two applications concurrently. And I will give you a little bit of example in the next few slides. To understand this, imagine that the platform is currently running an application, which is application A, and at time point T0, let's say another application B is enabled on the platform. So what Prism does is, from this point forward, it starts a local optimum and a global optimum optimization process. In the local optimization, it tries to explore all the previously saved mapping of B to find out a mapping that is reasonably best, but you can find it quicker because the design space has already been explored. And the idea is, at the minimum wait time, you will be able to schedule and start executing B. So application B is invoked by the user at a point, and we are at the process of making sure that B starts actually executing on the platform with a minimum wait time. And in this wait time, we explored the design space of B with all the previously explored mapping to find an optimum mapping that will give a reasonably good throughput from the application. But parallelly, it will also start a global optimization where it tries to find the best mapping for B, and I will give you a quick intro into it. So essentially, in the local mapping, as I said, it searches the saved mapping application B to find a good mapping, but at the global stage, it combines the graphs of A and B into a single big graph and then find the best mapping using the hill climbing optimization. Now, as the mapping size increases, or as the graph size increases, it will take more time for the hill climbing optimization to find a solution. That's why the global optimum may take longer time, but the local optimum is there to start executing the application to have a good quality of experience. So with that, I will move into the evaluation phase. So we use our in-house cycle accurate simulator for neuromorphic hardware, which was published, which is called Neuromorphic Explorer, and which is published at ICONS in 2021. I have provided the hardware parameters over here, and we have evaluated 20 state-of-the-art machine learning workloads, which is shown at the table towards the right. And we compare our approach with two state-of-the-art technique, SentryOS, which is an operating system for neuromorphic hardware, which was published in date 2022, and DF Synthesizer, which is also a baseline and is published in text 2022. So throughput-wise, we see that we achieve 2.2x higher throughput than baseline and 1.3x higher than SentryOS. The improvement is coming primarily because we explored not only the schedule of the computing actors, but also the communication actors. Throughput per watt wise, we achieved 57% higher throughput per watt and 42% higher throughput per watt compared to baseline and CentryOS respectively. And we also evaluate a few test cases, use cases for multiple applications, and we see that we could achieve a significantly lower wait time to start an execution. So as you can see, for example, just to give you a quick overview of this slide, use case 1, you see that it says that the local optimization takes 12 seconds. So it essentially means that use case 1 is a combination of BERT and mobile net. So what it means is that suppose that BERT is already running on the platform and you enable mobile net at some point X. Within 12 seconds, the application mobile net will be starting to execute on the platform while the global optimization continues. And after 223 seconds, the global optimization, that means the best throughput that you can obtain on the platform, will be available. But the important point here is that we try to minimize the wait time as much as possible so that we have a good quality of experience. So this brings us to the conclusion. What we did is we proposed Prism, which is a real-time system. It uses all system components to enable batch, pipeline, and operation parallelism, which are described in our talk. Prism is also able to schedule more than one application at the same time. We use 20 state-of-the-art machine learning workloads, and we show that Prism improves throughput and throughput per watt significantly and has a much shorter wait time to schedule and begin executing an application. So as I said, the GitHub code is already available. You can explore it.
Yeah, thanks
Thank
a lot.
Thank you. I'm happy to
thanks
take
a lot, Noop. So thanks for the excellent talk. So we are slightly behind the schedule. Let's take one short question from the audience. Yeah, Jens, please. Yeah,
no question here.
Okay. So, so if not, probably we can ask then, later. Then let's continue with our next talk. So thanks again, and let's continue with our next talk by Doron. And if you could start to share your screen, Doron.
Yep.
And it is about the reinforcement learning style algorithm for black box automata.
Hello?
Hi, Doron.
Yeah. You are screen sharing. Wait a minute. I thought there would be a problem. My screen is stuck. Do you have my slides?
Yeah, so I can share your slides.
Yeah, can you do that? If you just run the presentation, it would. Yeah,
no problem.
But I pre-recorded it, and I'll try to recover my video later. Okay, sorry for that.
That's cool. That's cool. So you are well prepared. Hey, Jens. So are you?
Hello.
Yes. Cannot hear you.
Oh dear. I have two of my students which can also share the slides. So there's a guy called Roy. If you can see him, I'm sure you could share.
Yeah, I see Roy.
Yeah, I'm here. I just can send you. We also uploaded the video to YouTube, so we can
just
share the link. And okay, just a minute.
Yes, you are muted. Could you? I don't hear you. What they are saying.
So I just remove all the videos from the slides, and then we can start once again. No problem. So now I have all the slides without the videos.
Without the videos.
Yeah.
No, but I cannot I cannot see anything. You see, my screen is stuck.
Okay, yeah, okay, no
That's
problem.
why I
Then
sent the videos.
I can also share with your video, no problem.
Okay,
That's
please
also,
do.
okay, no problem. Here we are. Yeah.
Yeah, that's it.
All right, then please go ahead. So somehow I cannot hear. Hello.
I cannot hear it too.
I can see the, well,
Me too. I see the screen, the slides.
it's a deterministic finite automata, which I know.
Yeah, I will. I will try, but I don't know how to do that. How to share the sound.
Yeah, I think Jens, if there is an option, Zoom asks you whether you want to share the sound as well when you.
Yeah, it's in the settings. Maybe here.
I think when right at the moment when you start sharing, there is somehow there's a checkbox usually.
Yeah, I see here on the lower left. Yeah, now I see. Okay, here we are.
By Itai Cohen, Roy Fogler, and Doron Peled from Bar Ilan University. We want to learn a deterministic finite automaton. A deterministic finite automaton is a 5-tuple consisting of the following components. Q is a finite set of states. Sigma is the finite set of input symbols, or the alphabet. Delta is a transition function from states and input symbols to states. Q0 is the initial state, and F are the set of accepting states. For learning, we know only the alphabet of the automaton and can reset it to its initial state and can make experiments. Automata learning is the task of learning the structure, that is the transition relation, of a black box automaton from a given set of example strings. There are two main kinds of automata learning algorithms. In supervised or active learning, the algorithm may experiment with the black box using a teacher, and the teacher has control on selecting the input symbols. In unsupervised or passive learning, the algorithm obtains a sample of the executions of the automaton and has no control on selecting the inputs. In this work, we'll present an unsupervised or passive learning algorithm for a finite state black box machine. We'll be inspired and we will compare our algorithm with two prominent learning algorithms. Anglin's L-star algorithm, which is supervised learning, and the algorithm Rpni, which is unsupervised learning. We'll present now some principles of Anglin's L-star learning algorithm. The algorithm uses a teacher that provides input sequences to the black box and obtains the corresponding outputs, which consists of zeros and ones for not accept and accept. The algorithm uses a data structure where the rows consist of reachability sequences and the columns consist of separating sequences. The reachability sequences on the rows allow accessing the states of the automaton. Different sequences may reach the same state. The distinguishing sequences on the columns allow demonstrating different outputs for the same inputs from different states. The table is separated into two parts by a horizontal line. The lower part extends the reachability sequences in the upper part by a single letter from the alphabet sigma. We say that the table is closed if the row for each successor of any reachability sequence in the lower part of the table appears already in the upper part of the table. If not, we move the row from the lower part to the upper part and add its successors using experiments to the lower part. Then we learn more accordingly. The table that appears in the slide is not closed. AAA is the successor of AA, and the row of AAA shows 1 and 0. But this is different than all the rows on the upper part, which are either 0 and 1 or 0 and 0. We say that the table is consistent if, when two upper rows are the same, their respective successors are the same. Otherwise, we add separating sequences that distinguish between these two rows. Then we learn more. In this table, the rows for epsilon and A are both 0, 1. But the B successor for epsilon is 0, 0, and the B successor for A is 0, 1. Thus, the table is not consistent. We can add B as a separating sequence to separate between these two sequences. When the table is both complete and consistent, and note that the table that appears in this slide is neither complete nor consistent, we construct a conjectured automaton based on the table. The states consist of equivalent rows. The transitions are based on successive reachability sequences. When the table becomes closed and consistent, we can construct a conjectured automaton MI. Then we perform an equivalence query between the conjectured automaton MI and the actual automaton. If they are not the same, a counterexample is given. Note that the number of queries required for an equivalence query is exponential in the size of the automaton. Now, given a counterexample to the equivalence query, the algorithm updates the table according to it and continues learning, generating then an automaton with more state, MI plus 1, and so forth. We move now to the Rpni algorithm. Rpni is a passive learning algorithm, and we have no control on the experiments. We first construct a prefix tree, or a trie, which is built from the provided examples. The nodes in the tree are marked with accept or reject, depending on the experiments. Then the algorithm merges nodes of the prefix tree, provided that the subtrees that start at these nodes are consistent with respect to the marking of accept and reject. And there are no merges left. The result is the learned automaton. Note that Rpni does not have equivalence queries, so the result may differ from the actual automaton. In this slide, we see a partially combined graph that is obtained from the prefix tree. The black nodes are those that are already processed. The gray nodes are the candidates for being combined. Now we want to check whether we can merge Q5 with Q2. We do that by looking at their corresponding subtrees. Since the subtrees for Q2 and Q5 are consistent, we can do the merging. So here we merge Q5 into Q2, and subsequently Q8 into Q3, obtaining the combined graph on the right. Let's look at the common principles between L star and Rpni. First of all, we need reachability sequences. They are organized either in a table in L star or in a tree in Rpni. Then we need to distinguish states. Either we use distinguishing sequences in L star or use mismatched subtrees in Rpni. Here's our idea. Can we calculate a value associated with each node in the prefix tree that will separate the reached states? The new learning principle that we try to adopt is related to reinforcement learning. In reinforcement learning, we learn to interact with an environment while trying to minimize some value. This value is typically the expected discounted cumulative reward. So it's kind of an average value which relates to the sum of rewards. We get a reward R1, R2, R3, etc. And we discount them because we cannot have infinite sums. So we discount the reward at each step. At first, we do not discount, then we discount by gamma, then by gamma star, etc., etc., where gamma is some value that is bigger than 0 and smaller than 1. Usually, the environment is a Markov decision process. Also, typically, we can see the current state of the environment, but this is not the case in our problem. The learning process may alternate between exploring new possibilities with probability epsilon and exploiting an already learned strategy with probability 1 minus epsilon. Basically, we learn to interact with an environment while trying to maximize a discounted cumulative reward through repeated Monte Carlo-based experiments. There are different methods for improving the current strategy iteratively. For example, the Q method, which is based on the Bellman equation and appears in the rather complex formula below. Note that this works when the current state is known, which is not the case in our problem. In classical reinforcement learning methods, a policy is a function that maps states to actions. This means that according to the strategy pi, we select an action A from the state S. We would like to obtain an optimal policy pi. We do that by calculating a utility function v of pi for the policy pi, where v pi of S gives the expected sum of discounted rewards from the state S using the policy pi. We then improve the policy in order to obtain an optimal one. Since we do not have prior information about the environment dynamics, we can estimate the utility function using Monte Carlo-style repeated experiments. We aim at learning a black box finite automaton. We cannot observe the automaton states. The black box randomly generates sequences of a uniform length, say 2 or 3 times the estimated size of the black box. An experiment contains inputs and outputs of the black box. We assume a fixed distribution on the selection of actions from each state in the sample sequences. The idea behind the algorithm is to separate the observed prefixes into clusters, where each cluster corresponds to a state of the black box automaton. The separation is based on utility values V of sigma that are calculated for each observed prefix sigma. The goal is to have in the limit that V of sigma equals V of sigma prime if and only if both prefixes sigma and sigma prime reach the same state from the initial state of the black box automaton. Let's look at the reward engineering for the calculation of the utility function. The reward is dependent on the current output, the subsequent input, and the next output. It's a bit complicated and appears on the slide and also in the paper. Unlike classical reinforcement learning, we only have an environment that we want to learn. We do not have an agent that needs to control it. As a result, there is a unique utility function v that we seek instead of multiple functions v of pi. We estimate the utility function by applying a Monte Carlo-based technique. The values calculated by our algorithm only approximate the limit values. So we look at the case where v of sigma is close to v of sigma prime. To separate the different observed prefixes, we cluster them using a density-based clustering algorithm. Each cluster represents an automaton state. Later, the automaton transitions may be inferred according to the observed sequences of the black box. In order to prove the correctness of this algorithm, we need to show that in the limit, the utility values for different prefixes that reach the same state are the same. Fortunately, this is not the case. We have found a counterexample. If we look at states S1 and S2, due to symmetry, they have the same utility values, although these are different states. This is true for any distribution of the transitions. In the previous slide, we saw that we failed at separating states when relying exclusively on calculating utility values. To obtain correct algorithm, we design a mixed approach with two variants, a look-ahead variant and a dual clustering variant. The idea behind this approach is to refine the utility value-based separation using a further analysis of suffixes from the same cluster. Here is how we achieve separation. An initial separation of prefixes up to a certain length is obtained based on their utility values, just as before. These prefixes are called kernel prefixes. In the figure on the right, these are the prefixes contained in the red box. By our choice of rewards, we are guaranteed to be able to separate accepting and non-accepting prefixes based on their utility values. Here's an idea inspired by Rpni. We can separate kernel prefixes that have the same utility values based on the consistency of the subtrees rooted by them with respect to the accepting, non-accepting marking in the tree. Now, given a long enough look ahead, this can guarantee separation.
As part of this study, we compare our variants with the Rpni algorithm. We experimented with 5 suites of examples. A full description of the examples can be found in the paper. The measures compared were the average learning time and the minimum number of samples needed for correct learning.
We used 5 families of examples for our experiments. We tested each family with different parameters and sizes. The families are the following. Cross is based on the example that was impossible to separate with our initial basic utility-based algorithm. Combination lock is an inherently difficult example to learn because only a particular combination leads to acceptance. Divisibility, there's actually 2 families. One checks that the number of A's and B's are divisible by some integers, and the other look at the divisibility of the binary representation. Parentheses checks that the sequence of input parentheses are matching up to some level.
As we can see, the utility-based approach may need more samples, but the learning time is faster in some cases. Let's take a look at the first row. The family of examples presented here is the cross automata. Actually, the first one was the counterexample for the naive approach presented at the beginning. The examples differ based on how many states they include. You can see that the utility-based approach takes about 5 times faster to learn than the Rpni. Now let's look at the second row. These are the combination lock examples. Unfortunately, in these examples, learning time is slower than Rpni algorithm, along with the larger number of samples needed compared to Rpni. This is because combination lock examples are accepted only in rare cases, as mentioned above. In contrast to the learning time, the Rpni algorithm always requires fewer examples for learning. This is because for correct utility-based values, more samples need to be generated before the clustering process. In general, we suggest that the Rpni algorithm should be more efficient for hard cases, like when accepting exclusions are rare. In addition, Rpni is more appropriate when the number of samples allowed for generating is limited. In the dual clustering approach, less information is used, so the learning time is a little bit slower, even though the average learning time may still be faster than the Rpni algorithm in some cases.
Let's conclude. We design a utility-based passive learning algorithm for black box finite automata. Experiment showed mixed results. We need more experiments, actually. In some cases, we learn faster than Rpni. In some other cases, Rpni is faster. Our approach seems to need relatively more samples to learn than Rpni. On the other hand, our utility-based approach has a better time complexity. Ours is quadratic in the size of the learned automaton versus cubic for Rpni. This fact enables a shorter learning time in some of the cases. Thank you very much. Do you have any questions?
An automaton.
Thanks a lot. Very interesting, very interesting. So recently I worked on extending, the Anguling's L star algorithm to learn BQ automata. So I have a question. So the algorithm that you compare with, so the black box automata that you learned, in the end, so are they equivalent? So the automata that you learn and the one from the one that you compare with?
Yeah. I mentioned at the beginning both Angling and Rpni, but at the end we presented an algorithm which is unsupervised. So we cannot have equivalence queries, and that's where we gain. I mean, we lose by not being able to check if it's equivalent. On the other hand, by complexity, our complexity is even better than Rpni, and of course, it's not the exponential complexity of the equivalence queries of Angling, right?
I know. Well, what I mean is that, okay, so you don't have equivalence query through learning because it's unsupervised, but the automata that you learn and the one from Rpni, have you compared them?
Yeah. So in general, both they are very close to the automaton. And what you need to do is you need to check for long enough sequences in both, and for a large enough number of sequences in both. And as my student was showing in the slide, in the comparison slide, it happens that if it's a rare event, like if accepting is rare event, then Rpni would prefer better with less sequences, or would be more accurate in the end result. But if it's not a rare event, then probably will do better than Rpni. That's kind of the conclusion.
Yeah. So I will definitely have a look into a paper. Thanks. So are there other questions? So if not, so let's thank the speaker again. And we are slightly behind our schedule, but it's okay. So I will, finish my session.
So it's okay. Thank you. Thank you.
I will give the postpone the problem to the next session, namely Dominic.
So I take control over my session now. Okay.
So at the end, it's my problem. So don't bother.
No, I have. So I have in fact noticed that so the next speaker, the first speaker for the new session is verification. Okay, and the next speaker is Surinder. Okay, he or she is there. I think the S.
Hello.
On the screen.
Yeah.
Hello. Yes. So.
Am I audible?
Hello.
Am I audible?
Okay.
Yeah, I can hear you.
Yeah. Okay. So sorry, you should just share the screen now, okay?
Yes.
And so the first talk is on a novel approach to real-time contract-based reasoning for hybrid systems. So go ahead. And I invite other speakers to prepare, okay? But
so my screen is visible?
yes, I see your screen, but it's okay. Yes, it's fine.
So my topic is a novel approach to real-time contract-based reasoning for hybrid systems. And the outline of the topic is as follows. So I will start with the motivation, and we'll discuss about existing techniques for static reasoning for hybrid systems. The corresponding problems in the existing techniques I will highlight, and what solution we have proposed in the paper, and the corresponding methodology for that. So which involves, Heuristic logic based contracts and the associated compositional reasoning technique I will throw light upon. And then the WCT based, real-time Heuristic logic rules, which we have described in the paper, and the associated, SMT encodings. And finally, we'll end up with conclusion. So any verification activity involves linear temporal logic. And when it comes to hybrid system verification, obviously linear temporal logic is again used. But it has, limitations of state space explosion. And the composition of, the LTL properties is difficult. Although it has been tried by many researchers, but it has not been so impactful. And to prove any LTL-based properties, we require, system or a program to generate traces. And finally, when we specify contracts using LTL or MITL or any language, so they anyway justify the properties whatever have been written, but they doesn't say about the last state of the program or the program trace. So based on these things, we are motivated to, delve more into it. And the existing techniques for static reasoning of hybrid systems, as I said, they use LTL properties and sometimes contract verification, again using LTL properties. For example, if we have in the paper, we have the running example of the train gate controller. So which specifies a train running on a circular track, and gate open and closes based on the train position. And the movement of the gate is controlled by a controller. And the equations governing the train movement is specified in equation 1, and the gate movement is specified in equation 2. Now, if we specify a contract using LTL, so it is, as an example, is shown here, which says that whenever gate is down and train is moving, then gate eventually opens. So the issues with this is such type of contracts are not real time. And even if we use clock cycles or we say timed LTL, this will also not suffice, because the fundamental problem with any LTL property is it cannot reason out, the last state of any program code or any trace of the program. Finally, if we do the compositional contract based property verification, so the semantics are not properly specified. And if we use Simulink, again, Simulink in itself lacks clear semantics, and it involves, different third-party tools, so which are again not properly specified. So we come up with a solution saying that we propose a real-time horologic-based contract definition and composition framework, which redefine and we redefine the contracts with the timing intervals. So this means that the contract, the property specified on the previous slide, it can be redefined as whenever a gate is down and train is moving, then gate will eventually open in some time, which is 110,000 clock cycles. The train gate controller system has a train component, and we specify the train contract as if a train position is between, let's say, 0 to 15 meter, then within 110,000 clock cycles, its position will be 23 meter. And similarly, we specify the gate contract, which says that whenever gate is down, it eventually opens within 110,000 clock cycles. So composition of component level contracts justify the system level contract. This is what we have claimed in the paper using the horologic rules, which are the real-time rules, and we have specified that in the paper as well. So based on these fundamentals, we propose our methodology as shown in figure 2. In the first step of it, we create a Simulink model, so which is based on the the contract definition of the system. In the second step, the Simulink model is translated into a new language which we call as SyncC. SyncC is a real-time language which is derived from a real-time language called PretC. Why it's not moving? The third step is we do the microarchitectural analysis of the program to get the assembler instruction timings. And we also derive the SMT encodings of the program by applying the WCT based real-time Hore rules, which we specify in the next slide. Finally, the SMT encodings are input to the SMT solver so that all the component properties are satisfied. And finally, we say that a synchronous parallel composition of all the component level properties satisfy a system level property. So before moving ahead, we give a background of horologic contracts. We say that a pair defined as CH equal to PQ as a horologic contract in which P is the precondition and Q is the post condition for any implementation program, let us say, which is designated by S. And S satisfies the contract CH if and only if the guarantees which are designated as Q are met based on certain precondition which are designated as P. Any horologic contract, say CH, is sound if the post condition is guaranteed, and mathematically we say that S satisfies CH. Example from our running benchmark, the train gate controller. The train contract says that if the train position is between 0 and 15 meter, then within 110,000 clock cycles, its position will be 23 meter. For this contract, the precondition is the train position, which should be between 0 and 15. And the post condition is the train position will be 23 within 110,000 clock cycles. And our train model implementation satisfies this contract, and that's why we say S satisfies CH. So now if component level contracts refine the system level contract, then the composition of refinements justifies a system level contract. So based on this claim, so we define the component level contracts and compose them synchronously in a parallel way. And we claim that the system level contract will automatically be justified. The proof of this has been specified in the paper. So as an example, we specify the system and component level contract for our running benchmark, and we specify CS as the system level contract, in which we say that CS is if a train is moving and gate is closed, then it will be open in 110,000 clock cycles, whose the precondition of this system level contract is the train position should be greater than 0 and gate should be down. And the post condition is after 110,000 clock cycles, so the gate should be open. And we also specify the train contract, which says that if train position is between 0 and 15, then within 110,000 clock cycles, its position will be 23 meters. The precondition for train is the train position will be between 0 to 15, and within 110,000 clock cycles, its position should be 23 as the post condition. And similarly, we specify the gate contract, which says that if gate is initially closed, then it will eventually open within 110,000 clocks. And the precondition says that initially gate is closed, while the post condition says that if the gate is closed, then eventually it opens in 110,000 clock cycles. We say that the guarantee of the train refines the system level guarantees. And we also say that the gate guarantees also refine the system level guarantees. And we also say that the preconditions of the the system and the train models the gate precondition. And finally, we claim that the conjunction of the component level contracts models the system level contract. So based on this background, we translate the Simulink model, which we had created, into our imperative language. So why we do this? We do this to do the microarchitectural instruction timing analysis. And the language which we have developed is the Sync-C, and it's a subset of, PRIT-C. So example snippet of our train component, which uses this language, is shown here. So it is the train model in very brief, which is a set of whole bunch of, if-else conditions. And in every if-else condition block, the train's position is evolving based on the equation specified in the first slide. Next, we define the WCT-based real-time Hore rules. So these are a whole bunch of rules, which are assignment rule, sequential rule, consequence rule, loop rule, function rule, rule for true synchronous parallel functions, skip rule, and rule for conditional branches. So these rules help us compute and guarantee the WCT of any program clause. For example, assignment rule says that whenever the assignment x equal to e is executed, then the time taken by the assignment is omega cycles. So this is certified that from the fact that the precondition, when precondition is met, the time is w is equal to x, and when post condition is guaranteed, then time consumed is x plus omega. So similarly, we guarantee and we compute and guarantee the timings of all the other, program clauses, I will say, like sequences or consequence or functions or loops. And then we use these rules in deriving our SMT encodings, which I show in the next slide. So the overall procedure to generate SMT encoding is, first thing, we use PTM compiler to get the assembler instruction timings as I specified previously. Then we use this WCT rules to arrive at the SMT encodings, which constitute the pre and post conditions. And then we feed these, SMT encodings to a solver. In our case, we used Z3 solver, and we code all the properties or encodings in Python, and we prove them. And once we are able to prove all the properties, then we claim that, meaning if those properties are applied on the Simulink trace as well, and if they are proven there as well, then we say that our properties are sound. As an example, to the listing 1, so we apply the derivation rules to obtain the precondition. We start from the bottom, meaning the last part, which is the post condition, and we move upwards to derive a precondition. Now the last block of the listing 1 here, it has an assignment statement. So we apply the assignment rule and we get this expression. So which says that if the time before the execution of the assignment is W minus omega 4, then once the assignment is executed and the contents are updated on the program stack, then time will be W. So this means that omega 4 is the total number of clock cycles required to execute the assignment statement and update its contents on the local stack. Now, based on this understanding, we derive the SMT encodings and the overall WCT, which is computed for any system. In our case, the running benchmark, it's the train gate controller system. So we do the assembly instruction timing analysis of every program clause, and we compute how many clock cycles are consumed or used in executing those statements. And then based on that values, we compute the overall WCT of the program. Now in this running example, so we have the system level logic based train gate controller properties. So we have specified 2 properties here. The first property says that train completes 1 circle in the worst case time, which is 118,144 clock cycles. And similarly, the second property says that if the gate is closed, then it eventually opens in 110,000 clock cycles. Likewise, we compute the horologic properties for the train gate controller components, that is the train component and the gate component. And then at a later, as a next step, we translate all these into the SMT properties coded in Python, and we prove them on using Z3 solver. So doing so, we handle all the problems which is specified in the beginning of the presentation, because the properties which are coded in this fashion are compositional and they are scalable, and we guarantee the hybrid system behavior in real time. And we are no longer dependent on the plain LTL level properties. I would like to conclude this at this point. So we have presented a novel real-time horologic contract reasoning framework for hybrid system models. So as I said that we have not used LTL to justify the system contracts, rather we have used horologic based contracts, which effectively reason the behavior of the hybrid system models. And we have justified all our properties on Z3 SMT solver. And this is our novel work and probably a first attempt in the direction where we use horologic contracts. Thank you.
Thank you very much. So maybe there are some questions for the audience. Yes, please, Reinhard. Reinhard, yes.
Well, actually, I was just applauding, but well, since you are calling on me, actually, one question I would have. So, would you compare this to timed automata, or what do you think? How timed automata specifications might compare in terms of analyzability for that kind of problem?
As of now, we have not done comparison with timed automata. But yes, as a future work, we can compare it. Besides this, as of now, we have arrived at the preconditions using the manual effort, and there needs to be some work done so that we arrive at the SMT encodings in an automated fashion. So these are the future works which we are planning to do.
Mm-hmm.
Okay, thank you.
Okay. I have one question. In fact, you use Z3 as a solver for checking your system, your models, and I was surprised, in fact, because I thought that probably it was you do not need, in fact, some kinds of solver for dealing with so real numbers. Okay, so in fact, it's because you are mainly working with discrete models.
Mm-hmm.
Is it right?
Yeah. Yeah. So that's the reason we have used Z3 SMT solver. And but in case if you're working with continuous models, then we should not have used that.
Because maybe I was thinking to the fact that you can express your first contract as in using in fact a continuous continuous model, okay, in a way continuous, and then to extract, to discretize, okay, maybe, but to check and to check the relationship between these models, okay. So it's because it's I don't know if it is effectively very complex to check, and if the models you have checked are very big, and how efficient are your verification, in fact.
So when you are you asking efficiency in terms of time, like how much time
Yes.
the mod
time, okay. Yeah, well, yes, or the size of your models, okay.
So with regard to the running example, which is the train gate controller, so the properties which we have written here, and when we justified these properties using Z3 solver, so the total amount of time which was taken is of the order of 20 to 30 minutes for the overall system. While verifying the component level properties, it was just, I will say, faster as compared to the system level properties if we run. So, but here our approach is, compositionality, and the claim is if a specific composition of the component level contracts is justified, then system level contracts will automatically be justified if the composition is correct. So, based on the component level property justification, it was super quick, and all the properties were verified, if I remember well, within 10 to 15 minutes.
Okay, thank you. Thank you very much. So I think that I see no question. Okay, so thank you very much again. So the next speaker is Alex. Somewhere Alex appear according to my.
Hello.
Okay, Alex. Okay, so you can maybe. So it's beating fast because it's the questions you are working with. Are hard. Okay. So it's a runtime verification for clinically interpretable arrhythmia classification. Yes. So you can go ahead, okay, for no more than 20 minutes.
No more than 20 minutes. Perfect. I can work to that.
Okay.
Hello, everyone. My name is Alex. So this morning my time, I'm presenting runtime verification for clinically interpretable arrhythmia classification. First, I'll go through an introduction talking about setting up the talk for today. Then we'll talk through methodology, finally some results and conclusions. First thing, we're talking about ECGs, so electrocardiograms. These are a body surface measurement of the electrical activity of the heart. They form, a single heartbeat forms this beat on the right-hand side, which consists of 5 waves, P, Q, R, S, and T. The QRS are generally grouped together as the QRS complex, and a clinician will use the shape and the timing of these waves, both in relation to one another in one beat and in relation to other beats, in order to classify your heart as healthy or otherwise, specifically looking for a range of different arrhythmia. The traditional approach is to go to your GP clinic, have yourself hooked up to an ECG, have one recorded, and then have it later interpreted by a clinician. Naturally, this takes a bit of time, and unless you have a good reason, they don't get done. They don't get performed. So recently, both Apple and a company called AliveCore have released FDA approved ECG tools. These are both approved only for the detection of atrial fibrillation, which is only a single arrhythmia, but both are consumer accessible ECG tools to provide some preclinical screening for arrhythmia. Both of these approaches are machine learning approaches, which is great. You get a whole lot of data, throw it into a black box, and it spits out pretty good answers. we propose perhaps looking at it from a different angle, looking at formal approach to this, wondering if we can produce equal or better results. Benefits here being, firstly, that it's a white box approach, so we can explain how we came to our conclusion. We don't need extensive training data because for a number of arrhythmia, there is not a huge amount of training data, which means it's very hard to train a black box machine learning approach. And the other thing is that a large majority of the work focuses on a single arrhythmia, so we attempt to look at a range of arrhythmia. I'll talk through my methodology now. So the first thing is we needed to develop a set of formal specifications. And the approach that we took to this is using the approach that a clinician would take to read your ECG. So effectively, we have taken a method in which you teach a student how to read an ECG, and we've encoded that as a formal specification. Then we take those specifications, which are timed automata, which I'll talk about in a moment. We take them and synthesize runtime verification monitors so that we can then detect these arrhythmia in real time. We do this for a range of arrhythmia, both atrial fibrillation, premature ventricular contractions, and ventricular tachycardia. So for our arrhythmia specifications, we use timed automata. A TA is a tuple of a set of locations, an initial location, an alphabet sigma. In this case, for this example, QRS start and QRS end. That refers to the beginning and the end of that QRS complex I talked about at the beginning. We have a single clock in this example, T, which is used to time the width of this QRS beat. The accepting locations in this case are location 0 and location 1, and non-accepting are locations 2 and 3. So what we do is we effectively take the arrhythmia feature that a clinician would look for, and we encode that as a timed automata. As I said before, we look at premature ventricular contractions, ventricular tachycardia, which is fast, numerous PVC beats together, and we also look at atrial fibrillation. So that's the one that the Apple smartwatch now is able to detect. For the purposes of this talk, we'll just focus on premature ventricular contraction because each feature, or rather each arrhythmia, has a number of different features. For each one, we introduce a different TA. 20 minutes, don't have time to talk about every single one. So premature ventricular contractions are clinically classified with two features. The first is a wide QRS. So if we look at this trace in front of us, we have 1, 2, 3, 4, 5, 6 normal beats, sinus beats, and one labeled premature ventricular contraction. So you can see, comparing to a very wide beat. The second is that the P waves are missing. So these little pre-QRS complex waves are P waves. And in the case of this premature ventricular contraction, there is no P wave. So the clinician would be, in classifying this, looking for both the very strange morphology and the missing P wave. We take these two features and we produce timed automata for them. So the first is a wide QRS beat. As the QRS starts, we reset our clock. When QRS ends, based on the value in that clock, which in this case is milliseconds, if it's wider than 120 milliseconds, which is the clinical definition of a wide beat, we move into the non-accepting location. We remain in non-accepting locations until we receive a QRS complex that is less wide than the clinical definition of a wide one. So that captures the wide QRS detection. The second policy, which is really nice and simple, is just to capture missing P waves. So at first we start location 0, we receive P or R and move into the appropriate location. We receive an R beat after an R wave. After that, we expect to see a P wave. That would keep us in the accepting location L2. If, however, we receive an R wave, that means we've received 2 R waves in a row, which indicates that we've missed a P wave. So then we move into location 3. We then take these individual specifications and we synthesize runtime monitors. So the policies that we've just talked through are here, and we produce this complete system where we have the runtime monitors, which are taking as input the ECG events. So that's the P, Q, R, S, and T waves, which we signal process from an ECG and provide into the runtime monitor. When the underlying policy is not accepting, the runtime monitor produces an alert so that we can act. Our monitors in this case are only producing 2 outputs, either currently accepting or currently not accepting. We do this for a number of reasons. Basically, we don't have any trap locations, and this is because in general the ECG that you capture is ongoing, can continue for as long as a human's life, for example, and you only get a snapshot of that. So you can only truly classify part of an ECG. You can't ever classify a full ECG. So we don't say that a person has the arrhythmia forever, because they may display it for 5 seconds and then no longer display it. As we use multiple features to classify an arrhythmia, so we have multiple policies, we compose our individual monitor verdicts using a merge, which, as the clinician approaches to simply require both or all features to be present at once, we also require all to be present at once. So in order to classify a PVC beat as present, we need to have both the wide QRS and the missing P waves, both policies alert simultaneously, and when that occurs, we say the arrhythmia is present. If one of them was to not be present, we wouldn't say that the arrhythmia had been detected. And this allows us to, in arrhythmias that may continue for a duration, we would label the start and the end of that period of arrhythmia. So we'll now talk through some results. One of the challenges with some of the black box approaches is that you need a fairly substantial amount of training data. So what we've done is we've captured traces from a range of clinical databases. Very commonly used is the MIT BAH database. This contains a range of arrhythmia. We've also used the atrial fibrillation database, which is specifically focused on atrial fibrillation, the CPSC dataset, and a subset of the AAEL dataset. So we take these and we produce them, provide them as input to our system as a way to kind of test if we were to take this to an embedded system, how our system might perform. So we've extracted as many traces as we possibly could. You'll note, for example, ventricular tachycardia. There's only 9 positive traces in this particular data set, and that's one of the difficulties that a lot of the existing work experiences. There's only 19 examples of an atrial fibrillation trace. That's not a lot to go off when you train your data set. So in our case, we don't need to train, which is great. We're just looking at seeing how we perform. We do this through 3 metrics. Firstly, accuracy, which is the number of correctly classified traces over the total number of traces. The second is sensitivity. So this is your true positives over true positives plus false negatives, and specificity, which is your true negatives over true negatives plus false positives. Our intention for this approach or this system is that it would be a screening tool, and so you're looking for a high sensitivity. You're less worried about the specificity in general. Now, this is an important point to make, is that one of the challenges of comparison is that the existing work tends to pick and choose from these metrics which it performs well in and provide those results. So we've calculated these for all of our arrhythmia, and we have compared to those metrics that are provided by the existing work. So we compare in this slide a few different pieces of work. None of them are formal. In a few cases, you see that we require patient-specific training, where we're intending that we would not require any training at all, be it population training in these 2 cases, or patient-specific training. We intend to have a model that works generally for the wide population. The second relevant point is real time. So we aim to produce a device that you can kind of like your smartwatch. You put your finger on it, record your ECG, and get a result very near real time, if not real time. And a number of these approaches require you to collect some data, take it off, train it for a few minutes, and then you can subsequently produce results. Which, if you don't display the particular arrhythmia in the training data, how will it detect the presence of the arrhythmia? And in some of these cases, for example, ventricular tachycardia, this occurs for more than 30 seconds. It's a medical emergency, go to hospital sort of thing. You don't want to be training while you're figuring that out. So yeah, we're looking at a tool that doesn't require that. So we'll now look at our detection of atrial fibrillation. We can see that our work performs similarly to the existing pieces of work across accuracy, sensitivity, and specificity, or a little lower on specificity in this case. In the second piece of work, premature ventricular contractions, we perform again similarly. And this is only in accuracy, as the existing work didn't all present other metrics. But in the paper, we have full results for all metrics. And finally, ventricular tachycardia. Again, we perform similarly to this piece of work here. I should also point out that in the full paper, we discuss in some cases the training data and the test data used is not made public. They'll say we used 100 traces from unknown source, which makes true comparison challenging, and that's why we've elected to cover as many different clinical databases as possible. I'll now talk through some conclusions. So first thing is our contributions. Firstly, we believe this to be the first time that arrhythmia features have been specified formally as timed automata. We have comparable performance to the machine learning approaches with results that can be interpreted. So when we were talking before about those individual features and the merge block, what we can do is we can say to a clinician is we can say, we think it's atrial fibrillation because we detected this feature and this feature, which gives them something to look for and perhaps starts to demystify the black box of machine learning to kind of counter that. Why have you told us that it's this? I don't think it is. We have a step towards explaining why. The other thing is that our approach is being a runtime monitor is ready for implementation as an embedded system. I have talked through a bit of the difficulty in comparison with existing approaches, both in people using data sets that they don't make available and picking metrics that look really good for their work. So we've tried to cover our bases by doing as much of this as we can. The most significant limitation throughout the work has been the signal processing. Clinical databases tend to have nice clean ECGs. In the real world, there's noise, and getting rid of that noise is a challenge. So where our mistakes, where our errors come through, that is due to in most cases the signal processing missing a wave, for example. So as our future work, which is actually currently underway, we are taking the system and producing the embedded device with a tool here that has a single channel ECG. We then provide that through to signal processing and perform all the same monitoring that we were already doing in this work. So to see if we can overcome that signal processing and the real world challenge. Thank you.
Thank you very much. Okay, so is there any question in the audience?
I would have.
Okay, please.
So yeah, pretty cool work. Have you ever thought of combining your approach, that means the timed automata, with machine learning? Because you should have parameters in your timed automata, and in principle you could use machine learning to optimize all your parameters, and maybe this would improve your the performance of your approach, but you still have the white box, yeah, and everything is explainable.
That's a really good point. We haven't actually considered or we have in earlier work we did consider using machine learning to parameterize. Our concern was if it required patient-specific training, that we would lose the benefit of it being a ready-to-go tool. However, I think you raise a very good point. In some cases, so you would have seen in my example, we used 120 milliseconds as the definition of a wide QRS beat, which is the quote clinical definition. However, those don't hold across all populations. So where our parameters are potentially not performing as well, absolutely looking at a data set to produce a machine learning algorithm to determine those parameters would be a great idea. Again, if we could find enough of the clinically labeled data. But that's the challenge of all machine learning, right? You've got to have the data.
Yeah, and so what do you mean by traces? So what means a trace? It's a recording of a certain length. I think it's on slide 17.
Let's go back. So I assume these ones here?
Yeah. What is a trace?
So in our work, we've taken a 10-second trace in each case. These are, depending on the data set, sometimes subsets of much longer traces, where someone is set up with a recording device that they wear for 24 hours or 48 hours, or it could be a recording taken in a clinical setting for 10 seconds.
Okay, yeah, thanks.
Okay, maybe I have a question. Do you know, so I work on these topics of, first modeling, in fact, the pacemaker, and second, modeling the model of the heart, okay? Do you think that you can use, in fact, and people use also the UPAL for producing a model of heart, okay? So do you think that it can help you to validate your approach, or it's something that is not useful?
So we would. Are you suggesting that we connect the monitoring to a model of a heart?
Well, yes.
Yeah, that's.
I know one model by people from Carnegie Mellon, I think, or maybe no, not CMU, not from Philadelphia. So maybe it's. Yes. And it was done using, in fact, UPAL. Okay, I think we did something. We did a model with FNB, but it was not executable. Okay, and then UPAL was much more useful. Okay, I think so. I don't know.
Yeah, so I think we definitely can connect it to a heart model, and current honors project is looking at that, where we take an existing. We have a cardiac cell model done by Nathan Allen during his PhD, where he did hybrid automata models of the cardiac cells, and then is able to produce a fairly high fidelity model of the heart. We then take that, produce an ECG, which we can then signal process and run through our model. That work hasn't been completed yet, but the principle of connecting it to a heart is a really good way to, without necessarily having the clinical traces, test if your specifications work. Though you have to be careful that your parameters for your heart model reflect reality and not just the same features that you've used to describe your models, or else you're just checking yourself, and there's not a huge amount of point there.
And do you think that your techniques of using, in fact, runtime verification in this way can be used for other tools, other medical devices, or other organs?
Not other organs. I haven't thought about other organs. Potentially, if there's a way to measure them
问问题
from
也不会
from
太
say
问啊，我要听不懂还挺麻烦。
body surface signal, then possibly. I think there's been some electrical modeling of the gut, and so possibly there could be an application there, but not something that we've looked at this point.
Okay. Okay. So thank you for your talk. Okay. Thank you. Bye.
Thank you.
So next, last speaker for the session is probably there, I think. I don't know. It's a Ricky, maybe. And he's the last speaker for the session. Okay. Please
Can you hear me?
And so, okay, you can, please, it's, yes, okay, it's okay. Okay,
Yes.
go ahead.
Okay. I'm Rpni Hu from Beihang University School of Mathematical Sciences. The title of my paper is Reach-wide verification for time-varying system with uncertain disturbance. We will introduce our verification method in this aspected motivations over and under approximations of reachable set, avoidance reachability verification, examples and future work. First is motivation. Reach-wide problem is a crucial issue in various realistic applications, such as managed area vehicles and automatic cars. Take the case of auto-piloted control system. The car should collect traffic information and automatically adjust speed, which need to calculate the reachable set of the car, but current technology is not capable of reaching fully automated. Notice that it is impossible to obtain the exact reachable set in general, especially for non-linear system. In most cases, it is practical and convenient to find over or under approximations of the reachable set instead. Over approximations of reachable set can be used to prove that the system avoids unsafe set. And on the other hand, under approximations of the reachable set to prove that the system reaches the target set and can also be used for qualification. In order to avoid the unknown situation, we need to design more accuracy approximation and verification method for reachable set. Recent years, numerous methods has been proposed for reach-wide verification. This method often use Lagrange method, which follows the flow of system, or Euler-ring method, which models the dynamics of system by looking at how it flows through fixed sets. In this paper, we investigate the reach-wide problem of a class of time-varying analytic systems with disturbance described by uncertain parameters. The contribution of this paper, we introduced the evolution function for the system with given disturbance parameters, whose Taylor expansion at time t can be used to exactly describable the reachable set and connect it to the concepts of maximal and minimal reachable set of the uncertain system. By using partial sum of the series expansion of evolution function, we provide a remainder estimation-based method to obtain over and under approximations of the evolution functions. In this way, we can handle systems with rational and even triangle matrix functions. We design a numerical quantifier elimination-based method for verifying the reach-wide problem, which can handle time-varying obstacle set and the target set. In addition, if the system is robustly avoidable and reachable, our algorithm can definitely terminate with true. We consider the time-varying analytic system as follows: the equation 1. Therein, X is an n-dimensional vector. D belongs to Rn as a domain. U is an m-dimensional bounded disturbance parameter defined by U. Is defined by this curlicle U. It belongs to Rm. and f is an analytic real function. The solution of the system is defined as phi t, where x0 is the initial state. For conveniently, we define the time interval as t0 minus capital T and to the t0 plus capital T. And we denote the initial set capital X0 by sub-zero level set mu g. EDS capital X0 equal to mu g equal to the set of x such that gx less than 0. We define reachable set starting from the initial set of the states as follows. By given the 0. Since we can't specify the disturbance U0, we further define maximum and minimum reachable set as follows. It is clearly that the relationship between the maximum and minimal reachable set within the time interval t0 to t0 plus t is defined as this. So the computation of the maximum and minimum reachable set can be converted to finding reachable set for all u and t. We propose the reach wide problem with given target set RAT and obstacle set RAO, which is also called the sweep wide problem. It can cover the target site without, and we also consider the time-varying reachable wide problem. By using the analytic solution of the system, we introduce the evolution functions as follows to characterize the reachable set. The relationship between reachable set and the evolution function can be illustrated as follows. So a sub-zero level set of evolution functions is the reachable set. Then we can compute evolution function to represent the reachable set. However, evolution function, which is generally accessible. Alternatively, we consider the Taylor expansion and named T expansion. Moreover, for computation, we define the nth partial sum of the T expansion. Then we provide a remainder estimation-based method to compute over and under approximations of reachable set. For this, we introduce the following theorem, which can compute the remainder of the n partial sum. Moreover, for R xtu according to previous equation, we can construct a function trace n xtu as follows, where mi is defined inductively as this. Takes u as a parameter, it is clear that trace n equal to evolution n. For our proposal, we first define over and under approximations of functions as follows. This is the value of a function is less or greater than another. Thus, if we can find the upper and the lower bound of m, we can estimate the remainder. To arrive at over and under approximations of evolution function, we need to fix a set S as first. And consider that the function m contains phi t minus r. So we use the information from the backward reachable set. Correspondingly, we have the following theorem for describing the over and under approximations of evolution function. Furthermore, if the Taylor expansion of the functions can coverage we can obtain a nice property of Hausdorff matrix between the over and under approximations of reachable set. And thus we can have the algorithm 1. For given FGT and the box B contains the initial set T and the designed precision epsilon 1, we design an algorithm for computing over and under approximations of reachable sets for all U. First, we call Cora to get an over approximations and named as bound of the maximum reachable set as S, and continue to get an over approximation named at the interval of the backward maximal reachable set of S as. Then, according to this, we can iteratively increase the degree n of the trace nxtu to and estimate the lower bound L and the upper bound U. Then generate over and under approximations with the designed precision. And then we can, based on the over and under approximations given by algorithm 1, obtain the sufficient conditions for wideability and reachability in as follows. If this constraint holds, then the obstacle set is wide. And clearly, we can use a similar method for folification. We can design an algorithm for reachable wide verification as follows. We first call algorithm 1 with the precision epsilon 1 for over XTU and under XTU and bound, and let bound as the box S used for 0. Then we use R solver with specified arrow bound epsilon 2 to deal with the constants. Further, we process the output of R solver as follows. If the interval of false is not empty, we terminate the loop and return the system may be unavoidable or unreachable. If the interval of false is empty, but the interval for unknown is not empty, implying that the precision is not satisfied, so we reduce both epsilon 1 and epsilon 2 and repeated the previous steps. If the output of our solver is only true, we terminate the algorithm and return the obstacle set and the target set is avoidable or reachable. Obviously, we achieve a correct judgment by constantly improving the precision. As a result, if the Taylor expansion of the function can cover it in S, and the system is robustly avoidable and reachable, algorithm 2 can always find the appropriate epsilon, such that algorithm definitely terminate with true. Note that for large time interval, algorithm 1 usually requires a higher degree n and thus a large number of terms to ensure accuracy, which makes it hard for our solver to find the solution. Hence, for performance improvement, we modified algorithm 2 to algorithm 3 with the time splitting technique, separating the given time interval into k parts with equal lengths, delta t equal to t divide k. One observation is that for small time bound delta t, evolution function can be approximate well in low degree n, so that the computation complexity of our solver can be considerably reduced. Meanwhile, the reachable set can stay close to the initial set, so that the corresponding S will be small, making it easier for computation. It is worth mentioning that during the time splitting, if we directly use the result obtained in the previous iteration as the initial of the successive iteration, the score of trace XTU will grow rapidly when the iteration continues. As a remedy, we design a simplification producer as shown in line 9 to reduce the score of the output from algorithm 1 in each segment, reducing the computational complexity for the successive iteration and scoring some precision in the final over and under approximations. Especially algorithm list all the terms in the results, trace XTU as a list P, and then compute an upper bound of the absolute value of each element in PES after sorting P by the upper bound of the in ascending order denoted as P bar, and we gather the term in P bar until the sum of the corresponding upper bound of the collected terms exceed half of 1 minus R delta epsilon and remove the previously collected terms. Finally, by adding the half of 1 minus R delta epsilon 1 to the over and under approximations, say the line 10 to line 11, we can return the approximations with precision epsilon 1. We show the performance of our method with 5 examples, and we show the example 5 here. It is we modified a 8-dimensional non-polynomial system with and we set the initial set and the obstacle set and the target set, and we can verify the system is avoidable and reachable within the time interval 0 to 1. The figure shows the target set, the obstacle set, and the obtained over and under approximations of reachable set corresponding to U and T onto the corresponding PX to PY planes. And in future, we will investigate the reach-wide verification of switched and even hybrid system with time-varying disturbance. Moreover, it is also interesting to study the control synthesis problem for avoidance and guaranteed reachability. Thanks.
So thank you very much. Is there any question? So maybe I have one question. So your technique of over approximation and under approximation is very close to Galois connection and abstract interpretation.
Pardon? I can't hear clearly.
Your technique of over approximations and under approximation is very close to what people are doing when they have, in fact, they are defining, they are approximating, in fact, some set of states by some kinds of yes, for instance, bioconvex, okay, and it's close to, so probably you are defining some kind of Galois connection.
Yes, we can reduce the epsilon, and for many loops, for year loops, we can continue to reduce the epsilon and make it more close to the reachable set.
Mm-hmm. And okay, I know some work on André Pletzer on defining invariant, okay, or differential invariant, okay, and is it close to this technique or for approaching for like the over approximation, okay? Because in fact, if your over approximation is too over, not enough precise, okay, maybe you may reach some point which are available, okay, maybe, I think. So my question is that can you tune your approximation?
What my approximation?
Your over approximation, if the over approximation is too over, okay, can you tune your approximation just by adding some constraint?
My over, I have compared with some other results in the paper, and we spend more times, but we were able to get good results for the most of the examples.
Okay, but it's I think it's extending some kinds of classical reasoning, but over a hybrid system, which is not a very simple stuff, simple job. Okay, thank you. So if there is no more question, okay, I thank you for your talk, and I thank everybody and for these sessions, and I close the sessions, and I give back the for the next session. I think. Please.
So then I will take over control for the last session. So the last session for today is, there we have two talks about cyber physical systems, more or less. And so I'm not sure who will present the first paper. Alex, is that?
Yep, I'm back.
Yeah, so you're back. So we gave you a short break here. And the stage is yours. So
great.
Take
Thank
it.
you. All right. Hello again. In the second talk, I will be talking about the runtime interchange of enforcers, looking at attack modeling for a drone platform. First, we'll talk through a bit of a background, talk through the problem space, then the methodology we took, some results, and some concluding remarks. Cyber-physical system security is an important realm we all understand, and this is largely because cybersecurity itself is increasingly important. More cybersecurity, more cybersecurity concerns become relevant as we continue to digitize our world. But this becomes even more important when we start applying these digital systems to physical systems. So we take a drone, for example. We have a nice computer-controlled or remote-controlled device, which is in our physical world able to both do good but also do bad if it is not safe and secure. So the consideration then becomes, how can we look after these physical systems so that they are not likely to be a risk for us if we're using them in our environment. So attack modeling is usually it depends on the angle you take, but a lot of the work in the commercial space looks at taking a system model, looking at potential targets, methods of attack, and the impact of those attacks. So you can do a risk analysis, and then you can start at your highest risk and start patching those risks, or start trying to mitigate them. This particular survey paper that I'm referring to looks at a huge range of different drones, from the off-the-shelf commercial ones you can buy at your local electronics store, through to military-grade drones that governments are using to perform surveillance and carry out attacks. So this paper considers a wide range of them, their uses, but it also looks at, in general, their weaknesses and defenses to those weaknesses. Specifically on a very common kind of prosumer grade drone is the DJI Phantom 3. This particular piece of work was able to demonstrate some attacks on it. So it's already a known problem that these physical systems, these drones, can be compromised, and that could have potentially a very significant negative impact. So we have drones for a number of good things, lots of video of events, deliveries even, with Google's project in, I think it's called Wing, delivering packages right at this moment, which is fantastic. You know, you dial it up and it's like an Uber for a package. They're also being used for search and rescue because you can fly them in higher risk areas where you might not be able to get a helicopter. And if the drone crashes, it's only the drone, it's not a helicopter full of crew. However, there are also opportunities for bad actors, both to interrupt the good, so say a package being delivered or live footage of a sports event, or to take a commercial drone and use it for bad. Importantly, how do we consider, or how do we check our drone? Say we're developing a drone. How do we see how it responds to different attacks? So we know cyber-physical systems are vulnerable to standard cybersecurity threats, but that they have wider consequences as they're interacting in our physical world. We know that they're used by both good and bad actors, and that they have a large attack surface. We also know that there's no open testbed for drone security. So what we aim to do in our work is look at this. Specifically, we look at how drones and base stations might respond to attacks, and we attempt to demonstrate particular vulnerabilities that are already known with formal attack models. So we develop a suite of attacks using a formal approach, runtime enforcement, which I'll talk about in a moment. And then we look at taking individual attacks and choreographing them to make more complex, complete attacks that make use of multiple smaller individual attacks. And this allows us to produce a range of attacks which we hope to then use to test how a drone responds. So the first thing we do is we need a tool to kind of test our drone system. And short of going and buying a drone, there is a simulation, an open source drone controller that allows you to simulate. So we make use of that. We focus specifically on the communication between the drone and the base station. A number of the weaknesses found in existing work is that the communication between these is often open, and that poses obvious risk. So we then place enforcers in to model these communication attacks. So our setup for doing this work is an open source simulator and communication protocol that has a whole lot of abstraction for controlling the sensors and actuators on a drone, with a nice way of basically an API for asking the drone to do things, so that we don't have to worry about battery voltages or the speed of a motor to get our drone to do what we're looking for. We can simply say take off, and it will sort everything out for us. So we take this setup and we see a drone. This is the example of the simulator. It provides a map. You can fly anywhere in the world that you'd like. Obviously, this is all just simulation, but it does cover a large number of the kind of parameters that you would expect for a physical drone. And the benefit of this is that if you wanted to take it and apply it to a real drone, you simply swap out the simulator component that simulates the drone for the controller on an actual physical drone, and the same code that you've written will work on a real drone. So what we do is we look at this communication, and we place our attacker as a man in the middle between that communication. So a drone is programmed for a specific type of mission, let's say a simple takeoff and land. The base station will provide the configuration to the drone, for example, take off to 10 meters and then land, and then the drone will execute that. We place our attacker in the middle, so then we could potentially interfere with that instruction. So we look at runtime enforcement briefly. This extends runtime verification, where previously monitors would raise alerts. They now become enforcers, where instead of raising an alert, they intervene, preventing the violation or preventing the violation from happening. So in a traditional sense, your enforcer is a safety enforcer. So we're looking at a a policy that would ensure that a bad thing doesn't happen. Let's say the drone doesn't, I don't know, violate a boundary in airspace that it's been cleared to fly in. The principle of this is that we can have a safety enforcer which is much simpler than our controller, so we can verify our policies in our enforcer with much less work than would be required to verify the controller. So this principle has been used a fair amount for safety, but what we do is we flip that and instead look at using enforcers to ensure a bad thing occurs. So rather than being a safety enforcer, it's now an attack enforcer, where our environment, which is our drone, and our controller, which is our base station, might instead, we could take an input and compromise that, or we could take an output and compromise that. This allows us to, with our man-in-the-middle attack enforcer, produce attacks and see how the drone responds. We consider 3 different types of attacks. The first is jamming attacks. This is where we could jam all signals, some signals. We could do it for a time period. We could switch it on and off. We could do injection, where the attack enforcer injects an output from the base station without the base station doing anything. Any form of control signal we could inject. And finally, we consider alteration attacks, where the controller might say, could you please fly to position A? And we would instead change that to position B. We used valued discrete timed automata for this. This is an extension of discrete timed automata where we have valued input channels and output channels, and this allows us to capture specific configuration variables like altitudes or locations, and then we can change those. So for now, we'll talk about jamming, where in general, when the drone receives a signal from the base station, one would expect it behaves appropriately. So let's say it says abort or land, the drone would respond. If we engage our attack, we could jam all signals over a specified period of time. So things like landing or aborting would not be sent through to the drone, so it might crash or end up in an unsafe location, like a physical unsafe location. So here's an example of a VDTA policy that captures jamming. Sorry, I'm just trying to move the zoom bars out of the way so I can see. So this is a simple example of a jamming policy that jams all signals between the period TS and TE, start and end of attack. The important thing to see here is that our enforcer would violate if the attack was not successful. So if any input signal if the input and output channels isn't an empty set during the attack active period, then the policy would violate. So this is what makes the enforcer perform the attack, basically making sure that it doesn't violate, which is a bit of a flip to usual, in that we want the bad thing to happen. That's great for individual attacks, but what happens if we want to look at more complex attacks where modeling them as one large VDTA policy will quickly become quite challenging? If you're trying to conceptualize multiple attacks in one policy design, this can become quite challenging. So what we propose is one overall attack controller and many attack enforcers. So multiple of those smaller examples with a manager that turns them on and off as appropriate. So to do this, we add in, we borrow a concept from, I think it's from Estrel, where we look at suspension. And effectively, when not active, the individual attacks stay in their location, do not increment clocks, they just wait. When they are told to activate by the attack controller, then they consider inputs, outputs, and increment their clocks. So the principle here being that we can effectively turn on and off attacks as the attack controller would like. So now we'll take a look at a an attack controller example. So this particular one is for 3 missions: a simple test mission where the drone takes off and lands, a delivery mission where it takes off from location A, travels to location B, drops off a package, returns to A, and mission 3 where it's simply asked to travel from A to B to relocate. So the attack manager activates different attacks in different locations as it moves through those missions. So for example, if we look at let's look at a simple takeoff and land mission. When configured for the takeoff and land mission, we end up in this location here, where the drone is waiting for a configuration signal that tells it how high it needs to fly. This is when we activate the alteration attack for altitude, so that when the base station sends the configuration with the altitude, our attack enforcer is active and it will change that altitude from whatever it's set to whatever the attack is defined as. In the results, you'll see some examples of this. But we also have ability to jam land signals, inject a land signal, and jam an abort signal that might prevent the drone from ending up. The controller might be smart enough to say, hey, don't land at this strange location, but our attacks would be able to prevent that signal from getting through and force it to land. So let's now talk through some of the results. So first we look at the individual attacks. So this is just for a simple takeoff and land where the drone is asked to climb to an altitude of 10 meters and then return to ground. So you see that is the standard altitude profile. As we add in our different attacks, we can jam the land signal to start with. So we remain at the altitude for a much longer period of time. We can inject an abort signal early on so that it doesn't ever reach its altitude. We can also alter the configuration. So instead of being told to fly to 10 meters, it flies to 15. This is a really good example of where you might be given clearance to fly to 10 meters, the drone flies to 15, and there might be something else in that physical space if we have a problem. The more interesting side is when we start to run multiple attacks at one time. So this example here is where the drone is asked to do those 3 missions, one after the other. The first is to take off to 10 meters and land. The second is to fly to a location B, drop off a package, and return to A. That's flying from here down to here and back. And then finally, to relocate to a new base station. That's this point here to this point here. So this is the physical 2D space. This is location, and this is altitude. So these match up. If we then engage our attack, first we have an attack that alters the configuration. It only flies to 5 meters. Secondly, the attack, when it flies to, when it is supposed to do a delivery mission, we change the location. So instead of flying to the delivery location, it flies to the attacker, drops off the package, the attacker gets the package, and then it returns. And finally, if the drone is then asked to relocate, instead of relocating to its new station, the attacker can have the drone fly to it and ultimately end up in the attacker's hands. In this example, obviously, the attacker could have taken it at the point of it dropping off the package, but for this example, they elected not to until it was relocated. So in conclusion, cyber-physical systems are increasingly at risk of being compromised with standard cybersecurity threats. Our contributions are modeling attacks on a drone platform as VDTA, running these as attack enforcers, and then composing individual attacks with enforcer interchange for more complex attacks. Future work, we intend to look at other automata as a alternative to VDTA, and also looking at this as a testbed for developing defense mechanisms, which perhaps we could do with the likes of a safety enforcer, runtime enforcer. Thank you. Any questions?
Yeah, thanks. So, first question from my side. Basically, I think that your approach is a bit more general than the title suggests. So what you basically have is you have a controller and you have an environment, and in between you can, yeah, you can place a man in the middle there in the communication part. But so that's a situation which is not, yeah, no, not special to drones, but it's quite general. So do you agree?
Yes, we definitely agree. For the purposes of developing a good kind of example where we can kind of figure out what attacks might make sense, and then see if we can express those formally, we had to pick a relevant kind of physical example. But yes, it absolutely could apply to more.
Yeah. So the example is perfect because you can really imagine what can happen. So, but a technical question: how does this attack controller, how does it choose between these between these different attacks, between these attack enforcers? So you say they can be suspended, but how is this managed?
This has to be defined by the attacker.
Okay.
Yeah, which is a which does require that the attacker obviously knows how to the drone system has to be a gray box, and that we have to know what sort of missions it's trying to do before we can describe the attack manager.
So we listen. What else do you want to know from Alex? Or any comments? Oh, the people are getting tired, it seems.
I'm only just waking up.
Yeah. It's getting dark here.
Yes,
still dark here. Hopefully we'll be light soon.
Okay. Then I just say thank you. Thanks for your talk, and here. And
thank you.
Then there is one person between us and the end of the program today. One left, but yeah, Robert, you are there, and
I'm here. Yes.
Yeah. Okay. So the stage is yours. So
the stage is mine. Okay, great.
Yeah, the last talk for today.
Right. I hope you have some energy left. Right. I'll just share my screen. And can you hear me? Okay.
Mm-hmm.
All right. Okay, I'll just jump into it. Okay, so I'm Robert. I'm a PhD student at Chalmers in Gothenburg, Sweden. So I will present work together with some collaborators where we sort of prototyped a language for writing sort of real-time applications for IoT devices. So I'll take you through that. So I'll just begin with an example, sort of showing a small IoT program that I sort of want to use here to make some points. So it's a very simple program. I need 2 buttons and 2 LEDs, and the program will wait for a press on either button 1 or button 2. And depending on which I press, it's going to wait for me to press the other button. And when I do, it's going to light up an LED. Depending on the sequence of presses, it's going to light up different LEDs. So I think about, in my experimentation, I use these boards. I'll have some specs listed later. If I were to write this in C, I would probably use a structure like this. I'd have a main function doing some boring initialization stuff, installing the button callback and initializing the LED. But the bulk of my program would probably be in this callback, since this is such a small program. The callback itself would sort of, if I press a button, it will check, okay, so have I pressed a button before? And in that case, is this a different press? And then I have one of the sequences, and I will light up one of the LEDs. Otherwise, I'll just remember what press this was. Right. So, but the thing here is that for this small program, I need to remember information between the 2 events. So there's sort of an issue here of running a sequential program over time, where I need to remember this information. I want to try to argue that, okay, this is a simple program, but using callbacks like this and global variables can quickly sort of grow, and it can become non-obvious if you have a bug how you should debug that, because you have callbacks that have sort of a non-obvious control flow and so on. Like, it's not obvious here that you're waiting for events. If you look at the code, there's a function that's called if I do certain things, like press a button. So the language we made, we call it Scoria. It's an embedded language, which allowed us to prototype it faster. We have a bunch of details about that in the paper, but that's not sort of going to be the theme of this talk. If I were to write this in Scoria, it would look like this. I define a program here that have 4 parameters, 2 buttons and 2 LEDs. And I say here that I want to wait for an event on button 1 or button 2. An event in this case is a write to one of the button references. And when I press the physical button, I trigger a write to this reference. Then this is a blocking call. So when I wake up here, I know that one of them was pressed. And I can make a test here using the function change to just check, okay, at this point in time was button 1 pressed. And I'll also come back to what I mean by at this point in time. If I did press button 1, I'll just immediately here wait for button 2. And when I wake up here, I know exactly which LED to turn on. I'm using the sort of control flow information here to figure out what the sequence was, and I don't need to coordinate using a global variable. I don't have any callbacks here, and it's much clearer what the control flow is of this program. So Scoria is intended to be good at 2 things. One is reacting to events, which I showed here, and the other is to talk about time. So time is a first-class object in Scoria, and let's say that I want to implement another very simple application, a signal generator, but I want the frequency of the signal to be controlled by another board sending Bluetooth commands. So the code for the board generating the signal on an LED at a set frequency, it can sort of be broken up like this. I can define the signal generator like this. So this function, it has a reference to the LED in question. So if I write to this LED, I will turn it on or off depending on if I write true or false. And I have a reference to some time value here, half period. So this function will use a statement called after. So after will schedule an update for the future for a reference. So here I'm saying after half period nanoseconds, give the reference LED the inverse value of what it has now. If it's on now, turn it off in a half period, and then I will wait for the reference. When I wake up here, I will immediately loop around and schedule the following event where I flip it the other way. Now the Bluetooth remote control for this, it looks like this. Sorry. There is a little BLE object here with a question mark. The question mark doesn't really mean anything in this case. It's just a variable name. But whatever I'm doing here is that this function will enable the scanning facilities on this board, and then it's going to wait until it successfully scans for a message, and then it will inspect the value. And depending on if it's a 0, it's going to double the half period, and if it's anything else, it's going to half the half period. So it's a very simple sort of remote control here. This little squiggly arrow here next to the half period reference, that's an immediate assignment, the sort of normal assignment you would have. The after statement is a delayed assignment for the future, while the squiggly arrow is an immediate assignment. Now, the final piece here is that we need to make sure that these 2 programs share the same reference to time. And I use I write the third part here called entry for this. So it uses var to create a reference, and then it uses fork to spawn concurrent child processes. So fork is the second of our 2 blocking calls in Scoria. Fork will resume when all children have terminated. So it's not enough that they're blocked, but they have to be terminated. So Scoria is deterministic, and everything that runs, every process has a priority. And fork will assign priorities to the children in descending order based on its own priority. So the signal generator here has the highest priority. It has a higher priority than the remote control. So a bit about time. So time is very important to Scoria. So Scoria is a synchronous language. Traditionally, if you have something like this called after, where or sleep or something like that, delay, where you schedule something for the future, that when that future event happens very much depends on where you execute it. If you do some heavy computation before you schedule it, you're going to be offset by that, the time it took to do that heavy computation. Since Scoria uses model time and implements this synchronous hypothesis, it doesn't matter what you do before, as long as it's non-blocking, because we assume that that takes 0 time. So time doesn't really advance in Scoria unless you have blocking calls. And so this program, we can compile it and run it, and we can check the frequency on using these oscilloscopes. So we can generate on this board here stable frequencies up to 6 point something kilohertz. We have some more details about that in our paper. So to come back to synchronicity here, so it's a synchronous language. And what I mean by a synchronous language is that it's a language where computations unfold as a sequence of 0 time instants. And I mean here that within an instant, time doesn't advance, but between instants we advance time. So I'll try to make that a bit clearer. So if we look at sort of other synchronous languages, we have the first 3 here are sort of these seminal synchronous languages, and I think they're all French also. French people seem to like doing this kind of research. It's very exciting. Lingua franca is a bit newer, and it's interesting. It's also sort of concerned itself with IoT devices and so on. So it's very interesting. With the exception of Estrel, you could also argue that these are data flow languages, and that means that you sort of define your data flow graph of your program when you write your code. But for these 3 languages, I'm not counting Estrel here. This is a static data flow graph, whereas in Scoria, this graph can grow and shrink dynamically using fork at runtime. Now, when you compile synchronous languages, what you end up with is a step function. It takes some state, and when you call it, it will sort of run the data flow graph, the computation, and it will produce a potentially modified state. And then these languages are clock driven. So that means that there's a clock that's ticking, and whenever it ticks, you invoke the step function, and however many, whatever time is denoted by the clock now, that's what the time will be within step. So time doesn't advance within the call to step, but between calls to step. Now this is a bit wasteful for IoT devices, these small devices that I'm thinking about. If you have a mesh network of small sensors, maybe a home alarm system, you don't want to change your batteries very often, and maybe these devices, they just wake up every now and then and take some measurement and talk to the rest of the network. So most of these points in time, you're not going to have anything to do. So it seems wasteful to sort of do these computations over and over again. So we implement something called the sparse synchronous model. So we have the same sort of traits here, where time doesn't advance within a call to step, but time advances between. However, we don't give meaning to every point in time. We can skip those points in time where nothing happens. So you can use after to schedule events for the future. And after you're done calling step, the runtime system can consult this priority queue of events to figure out, okay, but when in the future is something happening, and then it can sleep until then. And that allows us to have the processor consume less power, and we can extend our battery life this way. This is our hope. We haven't measured battery usage here, but we have seen that the boards go more idle, exactly as we want. Okay, so in a closed system, this makes sense, right? That we can create events with after, and then we can use this to figure out when to wake up. But what about events that we can't really foresee, such as, me pressing a button? The board doesn't know anything about when I do that, so it can't schedule a wake up for that. So this is our sort of world here, the runtime system. We have our step function, and the 2 major components that the runtime system uses during execution is, of course, a ready queue for processes. These are priority queues, and also the event priority queue. Now, if I press the button, what we do is this. There is an interrupt that triggers right when I press the button. Inside the interrupt, the only thing we will do is timestamp the event and write it to a buffer, a third buffer here that's sort of outside the runtime system. And when I write to that buffer, the buffer will wake up the runtime system if it's sleeping. And the runtime system can then, it's going to fetch the event from this third queue here outside the runtime system and carefully insert it into the internal priority queue for events. And then it's going to run step as if this event was scheduled from within. So it will wake up if it's sleeping to handle the event as soon as it can after doing this bookkeeping. This is how we react to I/O events in Scoria. We can also produce side effects such as lighting LEDs and so on. So how we do that is we can envision that we have a Scoria process that looks something like this. We talk about these references inside Scoria. So I reference to an LED. And this is a program that waits for another part of the program to write to the LED, write true to it, and that means turn it on. Then this process should be sensitive to that, so it should wake up, and then it should actualize this output on the physical LED. So we've handwritten these little handlers for a couple of different I/O devices, including the Bluetooth Low Energy scanning and broadcasting facilities. Now, and a follow-up question here is, how do we get the reference to the LED that we're using here to sort of coordinate all of this? And we have something we call a compile monad for that. So this is in Haskell where we talk about monads, but you don't have to know about monads for this for this talk. But what I do here is the compile monad runs and does sort of the initial setup of the program. So it's ran once. And what I can say here is that I can ask the monad for, okay, give me input 0, input pin 0, and it will give me a reference to that, to in my case, the button. I can also say, give me output 0, give me a reference to the LED 0. And I do get the reference here to the LED, but it returns a tuple where the second component is a reference to one of these handlers that I had here on the previous slide. And now when I have this, the only thing I have to make sure now is that this is scheduled and executable as the program is running. So we have a function for that that's conveniently named schedule. So schedule will populate the ready queue and define what that looks like as the program starts running. It assigns priorities the same way that fork does. So process 1 here has the highest priority and the handler has the lowest priority. And we have some details about priorities regarding, when should output happen. So inside step, I said that time doesn't advance. Now, what if I do I can make an instantaneous assignment, an immediate assignment to the reference inside of step. And then the question is, should this handler be scheduled then and the IO actualized during the invocation of step? Maybe it makes sense to wait until step is done and actualize the output after, before we advance sort of the time. And we came to the conclusion that there's not really a one-size-fits-all solution here. So we have some flexibility here and let the programmer decide how you should really prioritize the IO here. And the details about that is in the paper. Now about evaluation, I thought it was quite hard to figure out how to evaluate this. So we made this language and so on. Okay, now how do we evaluate it? So if anyone has input here, I'd very much gladly discuss that. What we did was that we wrote a few programs that we thought this could give us some, I don't know, interesting numbers and information, and we ran them. So I'll talk you through one of them here, and we have 2 more in the paper. So we call this one button to blink. So I press the button and the LED should light up as soon as possible. When I release the button, it should turn off as soon as possible. So in Scoria, we write this program like this. It's very simple. Just wait for the button to trigger an event and then just immediately reflect the value of the button to the LED. So these are all sort of binary values, right? Boolean. It's the button is up or down, or the LED is on or off. So I can write the button value to the LED in this case. Now, to have something to compare this to, a very sort of unrealistic program is one that's just polling, right? It's unrealistic in the sense that you don't write this program like this. But this tells us, okay, so if the processor is spending 100% of its time just trying to do this as fast as possible, this is how fast it will be. So this is our this gives us sort of a bottom line of how fast it could be. A more interesting comparison is that if we look at how we react to events like this from before, we had some setup here, right, with interrupts and this buffer outside the runtime system, and we had a semaphore as well to wake up the runtime system. What if we just shave off everything Scoria related here and just keep the infrastructure, but just immediately here, just do the thing, so we don't have a scheduler or anything here. This will sort of maybe give us an idea of the overhead of using Scoria, or the overhead that Scoria imposes here. Now, when we run these measurements, we get these results. So the polling one is of course very fast, right? Because the processor is very stupidly doing just this and nothing else. The interrupt plus semaphore one, the more realistic, it takes 31 microseconds, and Scoria takes 58. So there's an overhead here. Now, if we try to break this down and figure out what is taking time, so this is the measurement for the Scoria one, and the units here are microseconds. So as soon as I press the button, Zephyr OS will spend 18 microseconds just trying to find out which callback to invoke. Yes, sir, I forgot to mention that. So we're using Zephyr OS as well on the board. And then actually running the ISR takes another 9. So this takes quite a lot of time. These blue and yellow lines are present in both the interrupt plus semaphore version and the Scoria version. So if I want to shave down the difference here, I need to try to focus on the green line here, because that's the Scoria tick loop. So it does some extra thing, right? It retrieves the event from the buffer, inserts it into its internal priority queue, and it runs a scheduler and stuff. So there is some penalty here. Now we have a compiler for this, and I like compiler testing. So I've been, of course, we tested this compiler. So I wrote a generator for this program, so I can generate programs, random programs. They don't use I/O, otherwise they're random programs, and I can run them through the compiler. But then the question is, how do I know that the compiler did the right thing or not? I need an oracle here, right, to tell me that the compiler did the right thing or it did the wrong thing. So the first thing I did when I started working on this was that I read the already published paper about the sparse synchronous model, and I implemented an interpreter based on the semantic description in that paper. It helped me understand the semantics more. But now we all of a sudden have 2 ways of evaluating programs. We can interpret them and we can compile and execute them. So what we do here is that we instruct the program to be very sort of loud about what it's doing. So it's gonna yell, now I'm doing this, now I'm doing this, and they will produce traces, and we can compare these traces for equality. And if they differ, they have not done the same thing, and then there's a bug in one of them. If this is the case, we can try to shrink the input program and get a smaller failing test case. After this whole sort of loop is done, I will either have a vote of confidence that, okay, the compiler and interpreter at least behave the same way, or I'll have a minimum failing test case. The biggest downside here is that I don't, if I have the same bug in the compiler and interpreter, this way of testing won't find it. But I did find many bugs, of course, in my interpreter and compiler doing this. But it helped me a lot to understand the semantics. And with the sparse synchronous model paper from 2020, there was a runtime system as well as the artifact, and I did find 1 or 2 memory-related bugs in that paper. So harmless things, but still, it was fun to find those bugs using this kind of testing. Now, to sort of wrap up, as future work, I have some different lines of work to pursue here. Scoria is very limited right now in the types that it supports. It's mainly differently sized integers. So I'm a functional programmer, so I'd like to have algebraic data types. So I would like to add support for that. This language is embedded in Haskell, and I use the GHC compiler, which now has support for linear types. So I'm thinking that I want to try to give Scoria an even more type-safe API using linear types. It could be interesting to see how much we could get from this. Then, of course, improving the performance, experiment with different OSs than just Zephyr. Maybe we don't even need an OS. Maybe we can run it directly on the boards. I'm not sure. It would be fun to experiment with this. And then I would like to when I have the fancier types and these kind of things, I would like to write a larger case study. Maybe try to implement a mesh network where the devices where they use scheduled wake ups to talk to each other. So they agree on a time when they should wake up and connect and talk to each other. I think this would really stress test the sort of timing behavior of Scoria. I'm very excited about that. And that's all that I had to say.
Yeah, thanks for your talk.
Mm.
So I guess that there are a few questions.
Yes, I have a question.
Yeah.
So you are mentioning other synchronous languages, okay?
Yes.
And like Lustre or Signal or STRL.
Yeah.
And and you are mentioning at the end that you were in fact combining. So you have an interpreter, okay, I think.
Yeah.
And I would like to know, did you write an operational semantics or something? So some yes, operational semantics.
No, we've not done that.
Because in fact, so in a way, if you have written some interpreter, okay, it is based on it is your interpretation of your language, or how did you get the interpreter?
Right. So I wrote the interpreter. So in 2020 there was a paper published called the sparse synchronous model that presented this model of synchronicity, and Scoria extends this with I/O and some stuff, but mainly it's the it implement that sparse synchronous model is the majority of the sort of backend of this, and the interpreter is based on the semantics given in that paper.
Okay. Okay.
Yeah.
But what is so I haven't understood the difference between the sparse variant and the original synchronous variant, because from my point of view, if synchronous does not mean that you have a clock like a hardware clock which is triggered every whatever time step, but there could be just a few events. Yeah, if you just have an event, so in the next slide, if you just if you just see a trigger in step 1 and step 37 and whatever, yeah, so it doesn't make a real difference. Or what is
so in these languages you can talk about sort of the next point in time. You can talk about the next instant, whereas here you can talk about, okay, in 20 microseconds or whatever. It depends on your hardware what granularity you can
but your trigger could be in 20 microseconds. Yeah, then your system is triggered again, because the trigger could be external. Yeah, it's not in your so it's and I don't see a real difference here, because you can always trigger the synchronous program when something happens, and you don't trigger it when nothing happens.
Right, but traditionally these languages like Lustre and stuff have been clock driven. So there is this global clock, and you can define smaller clocks in terms of this clock, but you're still governed by this global clock that's gonna.
Yeah. So yeah, if you use them for hardware, but when you use them for software, then you only trigger them when there is really something to do. Yeah, and so that's basically the sparse. So what is challenging in synchronous languages, if you translate them to software, yeah, and you have all these causality analysis and these things here in the synchronous languages, so this is a real problem. And translating synchronous languages to software, is much easier if you have a relaxed model. So I don't really know the name, the sequential synchronous model, so where you can have several updates of variables in an instant, as long as these things do not interfere. And maybe you can have a look at these language variants. I can send you a few links, and then
Yeah, that
you
would
can,
be great. Yeah.
and then you can just check what might be usable for you.
Yeah, that would be great. Yeah.
Okay. More questions. Everybody is tired. Here, then I will close the session and also the symposium for today. Then we'll meet tomorrow again at what is it, 2 o'clock GMT in the afternoon with our second keynote, and yeah, see you tomorrow again. Yeah.
Okay.
Thanks,
Yes,
everybody.
thank you,
Yeah, for
thank you,
joining,
Jens.
and
Bye.
thanks for everything.
Thank you.
Nice day, nice week, nice night.